Bem, bom dia a todos. Bem-vindos todos. Nós estamos ao vivo, www.iea.usp.br/ao vivo e gravando. Perguntas deverão ser feitas ao microfone com identificação da pessoa. Coloquem os seus celulares no modo silencioso, por favor. Ao público online, as perguntas podem ser enviadas para iearesponde@usp.br. iearesponde@usp.br. O vídeo e as fotos estarão disponíveis na mediateca do IEA, www.iea.usp.br/mediateca, ou no canal do YouTube dentro de 10 dias úteis. Esses são os nossos avisos preliminares. Bem-vindos todos. Good morning, everyone. Welcome to USP in this beautiful, cloudy, or maybe sunny day. I'm Ana Paula Magalhães, and I'm assessor in the Research Provost Office, which I represent today. I'm also a professor in the Medieval History Chair here at USP. In the name of the Research Provost, Professor Silvio Canuto, I'm pleased to welcome all the fellow researchers from all over the world. I compliment the present authorities in the name of Professor Emanuel from IKISC, but as well important, my congratulations to the organization of this seminar, Professor Hamilton Varela, Professor Vivian Pellizzari, and Professor Douglas Galante here with me. USP has a settled tradition of collaboration with universities and research institutes around the world. And this has been the basis of our high scores on scientific publications and on scientific development. We believe that research gets people close and favors cultural changes. Research is, beyond knowledge and scientific improvement, a part of this major value named manhood. Excellence, responsibility, social purposes. Those have been the supports of the research that we practice here. I wish this workshop get our bounds tighter and increase our knowledge and our action in this important field of research. I hope you all have a very productive meeting. Greetings.
Well, thank you very much, Ana Paula. My name is Douglas Galante. I'm a researcher of the Brazilian Synchrotron Light Laboratory in Campinas, and also part of the research unit in astrobiology, NAP Astrobio, from here at the University of São Paulo, where I was graduated. And first of all, I would like to thank all the support given by the provost for the organization of this event, for the fantastic lecturers who accepted our invitation to come here, and for you, the public, to participate. And I would like to stress the idea of the strategic workshops is to really have an interaction with the public and to have an open discussion. So our idea, and I would like to stress, field of the origin of life in Brazil and at the University of São Paulo. So please interact, please interrupt us at any time we have time to discuss. It is our idea to have the feedback, even from online. So it will be a pleasure to receive all the questions, all comments, all critics, please. Please do. So we're going to open the sessions. We have 3 sessions for today, and we are going to start with prebiotic chemistry, and then move to very ancient life and paleobiology, and then move to the space and to the future, to seek for life elsewhere and astrobiology. So our idea is to move from the very small to the very big. Let's see how it goes. I think we're going to have fun. I think we can start without further delays. I would like to invite for this first session Professor Dima Zaya from the State University of Londrina, who will be the chair of the session. Thank you very much, Professor.
Good morning. My name is Dimas Aya. I am a professor from Londrina State University, Chemistry Department. I would like to thank you to Douglas Galante, Hamilton Varela, and Vivian Pelizari for organizing this workshop. I also would like to thank you, Tiago Altair. It was my angel, helping me a lot. Okay. And also I would like to thank you, Instituto de Estudos Avançados da USP, for this workshop. Today, I will be share this session, and we have 3 talks. One from Professor Michael Russell, one by myself, and another one from Professor Teresa Souza. I will read now a very resume de Professor Russell. Okay. Professor Russell works at Planetary Chemistry and the Astrobiology Section Jet Propulsion Laboratory. He acquired his degree in science at the University of London in 1963, and in 1973, Dr. Russell earned his PhD in geochemistry and geology at the University of Durham, England. He has several honors, awards. I will read only 3. Only 3. NASA Exceptional Scientific Achievement Medal, 2018, 2016 GPL Discover Award, and the 2015 NASA Honor Group Award, Ice World, and 2009 William Smith Medal Geological Society for contribution to applied geology. Okay, I read 4, no 3. He delivered several publications, and I will, only one here I will read. In this year, or in honor of Professor Russell, for his 18th birthday, was a meeting in alkaline events, okay, in Granada, Spain. Professor Russell published over 160 articles, and these articles have received over 4,400 citations. His more outstanding contribution was the submarine alkaline theory for emergency of life. Dr. Russell's lecture today will be about the hydrothermal events and the origin of life. Professor Russell, please. Thank you for accepting this invitation.
Sit down. What happens next? Do I get a show here? Thank you. Oh, do I sit here? Okay, sorry. Should I sit here then?
If you want to. If you want to stand up a little bit, if you want to walk out a little bit.
I just want to get the first slide. Well, good morning, everybody. I hope some of you were here yesterday because this is really for the workshop. And so as I've said earlier, please interrupt as you like. So I thought I'd just start with what I think are the initial conditions for the emergence of life. Now, if you're a physicist, you would never think of doing anything without understanding the initial conditions. But somehow or other, astrobiology doesn't seem to worry about that too much. Can't you hear me? Sorry. Do I have to do that again? I'm not used to this, sorry. I'm worrying about the initial conditions and how few people in astrobiology bother about the initial conditions of life. Now, a physicist would never think of doing anything without initial conditions, but we seem to take life too seriously. And I don't mean that in an ironic way. I mean that we think that it's about us, and therefore how do we come to be? But actually, it's about the universe and how we are an emergent structure of the universe. And I talk about us because we are quite a good example of life. We have, for example, iron, hemoglobin, and so forth, and I think iron was important at the emergence of life. So what I'm going to do, if you can all see these different pictures, is just talk you through how I see the initial conditions of life and how, in fact, it was kind of, on our planet, it just had to happen. It was, you could say statistically, deterministically, that it would happen. That wouldn't be true of many planets, I wouldn't say, but it's... what it does is we all live off about 1/2 to 1 volt. So basically it's about electrons. So if you don't think about the electrons, then you can't really get started. We are electrical motors, basically, and I don't mean this kind of in a derisive sense. If you think about each cell, each bacterial cell uses 1 million to 1 billion electrons a second. So you've got to take account of where the electrons come from. This is not Lego. You don't just assemble life by organic molecules that come from space, because there's too much junk there, for example. But, of course, as I said yesterday, and I always want to emphasize, is what does life do? What is its job? Now, in fact, that's the way to look about how we actually try to understand things when we're very young. One of the things we, as I said yesterday, we realize that things seem just to happen, but somehow or other, mother or father puts on a switch and it all happens. You have to be plugged in. So we need life to be plugged in, because you need those 1 million to 1 billion electrons a second for each cell. So that's another way of thinking about it. This is kind of a serious business about the evolution of the universe, and we happen to be the most complex, but rather inefficient or not large entropy generators, except in our own world. Of course, I mean, one of the things we're facing is just how effective entropy generators we are. In other words, how much kind of broken material we keep on producing from things that were eventually particularly low entropy to start with. So if we just start with this picture, and please interrupt if you don't understand. I'm going to sit down, it's easier, I guess. So here's the very earliest Earth that we know of, from about 3.85 billion years ago. Now there's a little bit of information before that from things like various isotopes. But I think one of the things I'm keen to say is I don't like the term Hadean, because it's pejorative. It kind of carries the view that it was a hellish place to be. Actually, 4.4 billion years ago, the world was a water world. And it really was an aqueous planet. It was, and the depth of the ocean was probably 4 to 8 kilometers. There was no land. You might have had a very occasional volcano coming out of the surface, but there was no land. The Earth is spinning about, a day lasts about between 12 and 7 hours. 12 and 17 hours. It's, the UV radiation is coming in almost 10 times as strong as it is today. You wouldn't want to be in the sunlight in those times. So, so we can take out some of the ideas about the emergence of life. There was no Darwin's pond. I think Darwin had a wonderful idea of evolution, but he said it's too early. He said in 1860, it's too early to talk about the emergence of life. One may as well talk about the emergence of matter. Notice he used the word emergence, because we are an emergent structure. And I would plead with you to change your title to the emergence of life. Origin rather says, I wonder how we came to be. But emergence gives respect to the universe about why we are an emergent structure after 13.5 billion years. So here's our planet about 4.4 billion years ago, and there would be plenty of carbon dioxide in the atmosphere. Now, as I keep emphasizing, what life does is to hydrogenate carbon dioxide. It adds hydrogen from water. Somehow or other, that hydrogen is freed from water, and it reacts with carbon dioxide to make a small but ever continuous amount of organic molecules on the planet. In other words, just because there's organic molecules on Titan does not mean there was life on Titan. In fact, it probably means there was no life on Titan. We've got a small but ever continuous amount. Why do I say that about Titan? Because there's no electron acceptors, because your electrons that you're coming in, I had breakfast, I had my breakfast, and now I've got to get rid of my electrons. There go some of them. That's some of my electrons going off in carbon dioxide. So I've got to get rid of the electrons. So I've got to think about that. So I need to breathe. Now, we all know I need to breathe oxygen. But in fact, all bacteria, overall, all life needs to breathe. Now, it might need nitric oxide or something like that, or nitrate. I think it's probably nitrate right at the beginning. But you need those electron acceptors. In other words, you need that material that will accept your electrons, an electron acceptor, an oxidant, if you like. So oxygen, CO2 actually is a mild oxidant. Nitric acid is almost as good as I will emphasize in later, is almost as good as oxygen. So perhaps we started the life with nitric acid coming from nitrogen and in the atmosphere, and CO2 being impacted by high UV such that you generate nitric oxide in the atmosphere. The nitric oxide dissolves into the ocean to make nitrate. So there is something to breathe there, nitrate. So that's going to be very significant. And it's got oxygen in it, NO3, not a bad amount. But we also need, of course, the reductants. Now, the world cannot help giving you reductants. Every time the water of the earth interacts with rock, you generate hydrogen. So all these hot springs you've ever heard of, I think, just about have hydrogen. And some of you might have heard of, some of them in Turkey, for example, emit methane. So you've had these everlasting flames of methane burning in our atmosphere. So hydrogen is easy to get from the planet because it's very reduced. Hydrogen is electron rich. The center of the Earth and the entirety of the interior of the Earth is electron rich, whereas the outside of the Earth is electron poor. So it's almost like a cell right there. You've got electrons in the middle, to the edge, and then on the outside you've got oxidized outside. Now what are those oxides? They are CO2. Probably an atmosphere, 10 atmospheres, maybe more. After all, Venus has 90 atmospheres of carbon dioxide, and it's our sister planet. So carbon dioxide automatically comes out of volcanoes. So there's the carbon dioxide, and that is, after all, the basis of life. The substrate of life is carbon dioxide. Everything you had for breakfast started out as carbon dioxide. So that gives you, so now we kind of get hold of what life's like. How would it emerge? Well, it emerges because there's such a disequilibrium between hydrogen coming out of the planet and carbon dioxide in the atmosphere, the relatively oxidized atmosphere, with H2O as well. Relatively oxidized. So we're going from reduced to oxidized, or electron rich to electron poor. So I think that's the way, so that's a disequilibrium. And you know that the planet doesn't like disequilibrium. We don't like it ourselves. We get stressed out because there's so much disequilibrium in our lives. But that's what drives us, actually. It's the disequilibrium that always drives us. That's what we should think about. When we think about thermodynamics, we should think about disequilibrium all the time. And then if we walk around our lives and think about our lives day to day, then of course it's about disequilibrium. And actually it's the things that you really love are far from equilibrium. You love those big waterfalls. And so long as the cyclone's far enough away, you love to watch it. So we are primed for disequilibrium. So the disequilibrium is between the interior of the Earth, which is electron rich, and the exterior of the Earth, which is electron poor. So now, many people think it's just a matter of chemistry. We could just solve the origin of life with chemistry. No, it's not chemistry. It's not chemistry. If it were chemistry, we wouldn't need life because the hydrogen would react with CO2 and reduce it to organic molecules anyway. But it doesn't. It's too hard. We know in our labs that it's very hard to produce CO2. We're desperate to try to do that because of the oncoming problems of the global climate change and so forth. We know it's too difficult. And that's why there's life, because it's so difficult to reduce carbon dioxide with hydrogen that life actually has kind of found the trick of how to do that. Now, what is that trick? It's got various tricks, and a lot of it's about physics. So let's have the way I see and I might just stick to this slide the whole time if we like, it's up to you. But so here we've basically got something called serpentinization. It's the only geological word you really need to know. Serpentinization. How does serpentinite form? There's plenty of serpentinite in Brazil, just about. You really can't hear me? Okay. Don't you have one you can put around your neck? No, I didn't mean to do that. So here's our early Earth, and it's an aqueous ocean. We've got something called serpentinization down here, which is what happens is if you have ocean floor and the water interacts with ocean floor, which it can't help doing, it falls down through the cracks, it oxidizes the ocean floor, and it oxidizes it with water. So it leaves hydrogen over. So serpentinization always produces hydrogen. Now, hydrogen, so that's our hydrogen, okay? But how does this happen? And it's happened since 4.4 billion years ago. It's always happening. Why? Because serpentinization is an engine. Okay, so really what we think about life is all about engines. So, in fact, the whole universe is an engine. A black hole is an engine for the galaxy. Convection is an energy for thermal heating, for example. Convection. That's the way physics solves thermal disequilibria. So if you have, but the chemical disequilibria is generated by physics. And that's a kind of chemical disequilibria, but as we hear, it's not soluble by chemistry itself. So how we look at the initial conditions. So we've got serpentinization, we've got an engine. I can go into how that engine works, but I don't have much time. So the hydrogen is produced at the surface at a vent on the sea floor. And the vent will automatically be alkaline because of serpentinization. I guess this is the whole point, is it? I'm supposed to be looking at this. Okay. So here we are, 4.4 billion years ago. We're in Neptune's empire. It's a water world, no continents. The hydrogen is coming up, but there are very hot springs as well. You've all heard of black smokers, I think, and those black smokers are bringing much iron, a lot of iron to the surface, tens of millimoles of iron to the surface. But they don't precipitate as black smoke on the early Earth. It goes into solution. So the whole ocean is a reservoir of iron. So we've got iron soluble in that early ocean. Can I just talk out loud? Can you hear me at the back?
Because of the transmission to the internet.
So there's a lot of iron in the ocean. 10 millimoles, or maybe more than 10 millimoles in the ocean. It stays soluble in the ocean because the ocean itself is somewhat acidic. So the iron is kind of nicely happy in the ocean as soluble. Sorry, I'm finding this extremely difficult with this microphone. I've never had to do this before.
I vote for you, okay?
No, that's even worse. You might propose. Okay. So the iron actually only precipitates on meeting. Has he got one? Has he got a?
Colocar ali do lado, na cadeira próximo, perto dele, talvez dele.
No, I don't want to do that. That's okay.
No.
I just thought you'd have one that's automatic around your neck. Even pop singers don't sing with this anymore that much, unless they're making love to the microphone. Okay, doesn't matter. Right, I'm sorry about this. I really am not used to this. So, I'm a human being. I like to be kind of wired in rather than. So, the iron is in the ocean, and there's nothing to precipitate the iron to start with because there's no oxygen to make iron oxides. And the iron only precipitates when it meets an alkaline solution. Now, the alkaline solution is being produced by alkaline hot springs in the early ocean. And one thing one can say about this hypothesis is that it actually predicted this lost city, which was found about 20 years ago now, which is an alkaline spring in the early ocean, pH of about 10 or 11, and it's got a temperature of about 100 degrees. So it's very nicely buffered in both temperature and pH, and it's got hydrogen in it. what happens is, as soon as the iron in the ocean meets the alkaline spring, then immediately you precipitate what's called white rust. White rust is, we have it here on the left, it's FeOH twice. So it's basically soluble iron that precipitates very quickly as soon as an alkaline fluid is reached. So we get a precipitate. So we get a kind of frustrating barrier between, yes please, it's frustrating, there's a frustrating barrier. Okay, so let's go back to thank you. So I get rid of one frustrating barrier, and now I can talk sensibly about another frustrating barrier. Right. You do it. So anyway, that was an example of frustration. And I don't mean that lightly. Beethoven was deaf and Monet was blind. Think about frustration. Think about creativity. Creativity only happens in frustration. Okay? That's true for our own lives. Dostoevsky knew all about that. You know, read books. Young people, read books. So here we are with a frustrating precipitate of ferrous oxyhydroxide. Okay, so first of all it's white rust, and immediately that turns into something called green rust. Now you're all aware of rust because rust is what happens to the bridges. However hard they try, the bridges always go rusty. If you go carefully through that rust, you'll find between the iron in the bridge and the red rust, there is something called green rust. Now the early Earth precipitated white rust, and that turned into green rust almost immediately. Now, green rust is a little more complicated. It's got a mixture of ferric and ferrous iron. So there's a mixture of valency. So here we are with the green rust. It's a ferric oxyhydroxide. It's got water in it. Now, here's a mineral that actually has water in it. Now, most minerals do not have water in them. Now, life has water in it. You know, that's not a bad start for life. If you're going to want to think about water, proteins have water. You know, the idea that we have to be dry to make a life is just ludicrous. We are wet. So we're not a dried up pool. We come from something really strong and dynamic, from an alkaline spring. And the two solutions are mixing. You've got hydrogen on the inside, methane on the inside. They're coming up. They're precipitating this frustrating barrier made basically of green rust, okay, ferrous oxyhydroxide, green rust with water molecules in them. And it's a layered mineral. I'm going to hope I get around to showing you that it's a layered mineral and water is trapped in it. And because of the ferric state of some of the iron, it requires an anion. It requires something like a carbonate or chloride, or sulfate, or phosphate to come into it. Now, we all know that that's quite nice. We like to have phosphate and chloride in us. So, yeah, I'll make that, because we're short, I'm going to make it, you know, let's use us as the analogy of life. So, and of course, one good thing about, one good thing about this is that it's like your hemoglobin. It can go from dark red to light red, so to speak, or from green to stronger green, as the changes from ferrous to ferric and back again. So here we've got a mineral that's actually rather like hemoglobin already. So in other words, now if you're in the initial conditions, and we know that life has got to start because of the disequilibrium between hydrogen and carbon dioxide, how could it be that life starts like that unless there was material around to use? So we need stuff that's actually there in a kind of junkyard, if you like, that could be used and make into engines. Now, green rust actually makes, to my mind, a wonderful engine. So here's the initial conditions. What do I need? I need disequilibrium. Okay, thermodynamically, I'm going to call that free energy. You know, I'm uneasy about the word free energy. You know, by the way, people like Boltzmann and Schrödinger and all those great people that we all respect. I'm just trying to think of one more. They said the idea of energy is ludicrous. You know, it's nothing to do with energy. It's disequilibrium. It's always disequilibrium. It's all about the entropy part. You know, it's the delta S. It's pulling, entropy is pulling the universe along. It's making it kind of more and more, if you think, complex, but only so it can break into ever smaller pieces, so to speak. So we've got to think, and we know that, by the way. We know how much mess we're making, and even the New York Times now tells us that actually we're making so much mess, we're in a climatic catastrophe or some such. That's entropy. That's what happens when you do very well at using free energy or disequilibrium and make the universe more relaxed. The universe, we might not think of it, but the universe is getting more relaxed because of what we do. So here's our free energy or disequilibrium, and here's the exhaust. You've got to have the exhaust. I'm going to run quickly to, there's two aspects about this, but do you see this I don't know if you see in Brazil, this, the Beverly Hills cops. Some of you might have seen them, have you? So you know how this guy gets away. Yeah, because, he's a sharp guy from Chicago. And he's dealing with Beverly Hills cops. It's people like Beckham used to live there. Sorry about that, but it's true. So in Los Angeles. And they're called kind of dumb cops, but Eddie, who knows what to do, and the cop's going to chase him. He knows that, so he goes into the store and he buys 2 bananas and sticks it up the exhaust. And off he goes, and of course they're stuck, because it's the exhaust that drives your car. It's the exhaust that drives your car. It's the exhaust that drives the universe. Okay? So that's the way to think about it. We're getting pulled that way. It's almost irresistible. That's why we're finding it so difficult to deal with climate change. It's so irresistible. Oh, there's still some oil. Oh, there's more coal. Oh, well, we better use it. I don't want to use it, but what would Australia do if we didn't have coal? So here's, so let's get back to this. Well, there's the other quick one. I worked at JPL for NASA. So I thought, well, I would like to be a rocket scientist. This is as close as I got. This is how a rocket works, or can work. You can use methane and hydrogen as the fuel, okay, because you've got to have fuel. But you've got to have an oxidant. You can use flaming nitric acid as a fuel, okay? And what happens is, it's quite clear what happens is, it's the exhaust that drives the rocket. No doubt about it. So here's life. So here's the exhaust. Off it goes, looking for life elsewhere, because we realize now it's not going to come into us automatically. But it's not very different, the emergence of life. It's just in water, so we're trapped at 100 degrees centigrade or a little less. And up comes the hydrogen and methane from the alkaline vent. Here's nitrate in the ocean, that's the oxidant, same one as here. And this actually makes, through the engines, it makes up biomolecules which can do the job better than green rust, better and better and better. Very slow little steps to getting better and better and better at making more and more entropy by reducing the internal entropy all that time. And finally you get the exhaust. And the exhaust is things like water, of course, always water, nitric oxide, probably acetate, and so forth. So the exhaust is automatic. You have to go to the bathroom. Bañero, you just have to. Unfortunately, that's what's pulling your breakfast into you. So that's the way the system works. So let's get back to this, and I'll take any questions on this. But the nitric oxide, by the way, that's the important one. That's produced from lightning, from CO2 and nitrogen, to give you the nitric oxide, and the CO2 dissolves in the ocean to make you carbonic acid. So that's the kind of system. Please, anybody has a question? Sorry? You have to have a microphone, pal.
Could you say a few words about the viability in this scenario of solving some of the old problems of the RNA world, the difficulty in forming...
The RNA world, the RNA world is like saying, I am going to make a car, and it's 1860, and first of all, I'm going to have a computer. It's rather like saying to the Jet Propulsion Laboratory, Jet Propulsion Laboratory, let's make computers in 1940. Instead of rockets. You have to have the rocket first. You've got to have the free energy first. Then you can get some information. There's information, as soon as you have something fairly... Look, this is a low entropy environment. We are living outside, relative to this, Sao Paulo is a high entropy environment. This is low entropy because of all the studies you've done, all your parents working hard for you, all the professors you're listening to. We've got ourselves into lower and lower entropy states, and now we're in a room all together. So this is a low entropy state. So that's why we hope we're going to have emerging ideas. But but I'm not talking about RNA, because what am I doing right now is nothing to do with RNA and DNA, or not much anyway. It's the metabolism. So I would say, yes, of course we have to make RNA, but it's not first. It takes time. In the first cars and the first steam engines, you had to have governors. They were mechanical. We need mechanical kind of information to start with, so to speak. For example, a pump. A pump is information. As long as it's operating all the time, it's information. So that's the way to think about it. It's not, the DNA, I'm not denying it, but my responsibility is to say, look, you can't start with a computer. You really can't. How did the computer start? It was weaving. Weaving was how the computer started. The Jacquard loom was how the computer started. It was stolen property for the weavers that knew how to automate the looms.
Very good. But my question is the following. Do you think that this could emerge from one single rocket like that, and this would give origin to all? Or do you think that it would be necessary several independent units like that to really start the whole thing?
Well, of course, it's a great question, and there's always the possibility that there were two origins of life, or two emergences of life. Because, after all, bacteria and archaebacteria have different membranes. They have some of their reproduction mechanisms are different to each other. They're so extraordinarily different. Could it be that they came from different vents? I'm not sure about it, and of course it's an open question. But I don't think it came, basically, to put it crudely, we won. Okay, there were probably thousands and millions of trials, billions of trials, and we happened to be the one that survived. So, the best way to think about Darwin's law is it's the law of natural origin. Oh, Jesus. It's the law. Have I gone off now? Am I still going? Yes. No complaints? It's the law of natural rejection. That's what we should always know. It's not it's not a good idea. Natural selection, it gets you into all kinds of political trouble to start with. And it's also, every student who's 18 thinks, or 19, they're going to make the world different because they're the best. Americans, they get a gold star. An American child gets a gold star for potty training, if you understand the term. Everybody thinks they're going to be just fantastic. But actually, let's get real. Suddenly we realize at the age of 18, the world's a tough place. It's hard work. We're walking this tightrope, and any time we could slip off. It's the law of natural rejection. So what I think, to actually empathize with your point, I would say that the emergence of life had to be a cooperative. But I would say this particular cooperative kind of won, or something like this cooperative won, and it's unbroken for 4.4 billion years. So yes, there were probably hundreds to thousands of original cells, and they're all cooperating, even to start with. And if I have time, I'll show how I think that's likely to be. But I got an idea about how to do this yesterday, listening to Nora Nofka, and I think perhaps because the young people here, I want to emphasize how I like to think science really works. So can I just run through this very quickly? By the way, that's the textbook membrane. The membranes in any life is nothing like that. It's full of protein. There's hardly any lipid. I just want to emphasize that. There's the protein, there's the lipid, there's RNA and so forth. Ribonucleic acid. So Nora showed this picture yesterday. Sorry, am I going over time? Nora showed this picture yesterday. Now, I've always known about biofilms, microbialites. Who doesn't these days? But she showed me this picture, and then she explained how she thought it all worked. And it's extra EPS. What is it? Out loud. Extra polymeric substances. So what do I do after Nora's lecture? This is typical the way a scientist works, is, wow, Jesus, I'm going to go to the Google Scholar and I'm going to look all this stuff up. So what do I look up? I look up how this stuff works. And here's a very easy example of how it works, that the bacteria get together and they exude, they secrete, or their waste product maybe, goes outside the cell and starts to bind to minerals and to each other. So suddenly they've got a cooperative, just rather like as you implied to start with. So here we've got a cooperative. Now, we know I think we know all about fractals and so forth, and how self-similar structures work in the universe, how the dunes in Sahara are... I'm going to leave it there. And yet I can look at sand with my children or grandchildren, and the waves are only this far, but I can't tell the difference unless I have a scale. So it's about scaling. So if this is a good scale for a biofilm, surely I can say, right, well, I mean, I didn't do this last night, by the way. We had this up our sleeves anyway. But now I've got a bit more of an excuse for saying it. Here's our green rust and McKenna-White, which is iron monosulfide, and they're all kind of getting together in an exuded amyloidal protein or peptide. So because I think that, and I haven't got time to show you, I think that you automatically get peptides, amyloidal peptides, you know, the prions, the ones that give you Alzheimer's and so forth, you automatically get that from this kind of system. And it exuded, and maybe that becomes the first kind of material of the cells, which are all together. So there's thousands and thousands of green rust, millions and billions, and there's hundreds to hundreds of these, and some of them are not rejected. Some of them are not rejected. So I got this idea from listening to Nora. That's how science works. We're listening to the people we can trust, always keeping our eye on next door. You know, so what am I keeping my eye on? I'm keeping my eye on things like electrochemistry, molecular orbital theory. You know, I'm a geologist, but I've got to worry about what's happening next door because we've done the initial conditions of life, I would argue. We know what they are. We know what was the problem. We know what the issues are. Now we've got to solve the next stages, and it's about the electrons, remember. But it's also about how you get communities and how they're going to automatically, actually part of the very excess of what you have. So, I mean, for example, I believe it's badgers or somebody will help me here. I mean, it's some organisms or some rats or something that they use their feces to kind of make a barrier against the outside world. You know, it's always use the waste product if you can. Of course, that's one of the tricks that capitalism is trying to work out now. How can we use the waste product? So, sorry, that was a rather long answer. Any more questions? Or maybe I've finished. I don't know. You stop me when you want to.
How sure do you think you can be about the accuracy of these initial conditions in the idea?
So as a geologist, I would say there is no problem whatsoever. Now, that sounds extraordinary, but we know what the meteorites are like. We know what they come, we know how we were made. We know that there's iron nickel meteorites. We know there's chondrites. We know there are magnesium aluminosilicates and so forth. We know all that. And we know that as they collapse, they will eventually make an Earth very much like this. So, and there's one vital point here that geologists should tell the rest of the astrobiology community if they don't know it themselves anyway. And that is that you've got to have a particular size of a planet. So, for example, our planet is made basically, the near surface of our planet is olivine, magnesium, iron, silicate, okay? Most of it. And that's what turns into serpentinite, which becomes a little more oxidized from the iron and hydrated. But, so basically we know that's the mantle. We know that's probably the mantle of Mars. And nobody's going to argue with me, I don't think, about that. Where they will argue is, why have we got carbon dioxide in the atmosphere? Now, that is weird. I would argue that you've got to have carbon dioxide in the atmosphere, otherwise there'd be no point to having life. So you've got excess carbon dioxide. Why have you got excess carbon dioxide? You've got excess carbon dioxide because our planet is big enough so that the gravitational strength, the densities are reduced all the time as you go deeper into the crust. And on our planet, when you get to about 650 kilometers down, olivine is now extremely uncomfortable. And it's being squashed, and it wants to become a mineral called perovskite. Now, perovskite's got calcium and magnesium and titanium and oxygen, silica, and so forth. So that doesn't seem that much like olivine. So how does this work out? Because if you've got no alumina, where are you going to get your 3+ material from, your 3+ ions, to Al3+. How are you going to get, if there's no alumina, how are you going to do that? Well, how you do that is you squash the olivine, and eventually the iron gives in. It dissociates into Fe3+ and Fe0. The Fe0 tends to go to the core, and Fe3+ is now in the mantle, and therefore it's relatively oxidized. It's so oxidized I mean, we think of it as reduced, but it's so oxidized that the stable state of carbon above 400 or 500 degrees centigrade is carbon dioxide. So it means all volcanoes on a planet this size will emit carbon dioxide. Now, we don't have to worry about the hydrogen and methane. That's going to happen. I mean, every planet's going to give you hydrogen and methane, and go to Titan for things like that. But you've got to have the electron acceptor, and the most complex, difficult one, the very happy molecule, is carbon dioxide. And that's what initiates an instantaneous life. So I don't think I would fight off, I mean, I don't know a lot of stuff, of course, but I would fight off anybody who would argue about that part. But you can try, of course. Yes, it's deterministic. I mean, it's deterministic, that's the point. Statistically deterministic.
Any questions?
See, that's the trouble with the microphone. It kind of keeps people quiet because they don't have immediate access to a microphone. Come on, give me a question. There's no such thing as a stupid question, says Einstein. Only stupid answers.
Thank you very much. Hello.
Hello.
I'd like to know, please, how do you put your ideas and couple with the heavy bombardment event during the Hagia?
There probably was no heavier bombardment. It's a myth.
Really?
Yes. So there was a bombardment. It was pretty continuous, but there was a beautiful paper, I think it's 2009, maybe 2013, by Moiges and I've forgotten his other name, begins with A. Somebody can help me. Basically, they show even if you had a heavy bombardment, then it doesn't make much difference to the temperature of the sediments, because the thermal conductivity of a wet sediment is so very low that the thermal wave wouldn't be able to kill off the deep biosphere at any time. You can have a heavy bombardment if you like, but of course, they were pretty tough bombardments. If it had been big bombardment, we wouldn't be here. So we know that there was always just a bit less. And I don't think anything would have killed. I mean, try weeding your garden or get rid of the mice. Whatever you do, it's very hard, or the child's nits in the hair. It's very hard to get rid of life once it gets started, because it's a going concern. So I have no worry about the heavy bombardment.
Thank you.
That is rather a personal view, by the way.
Any more questions?
You're letting me get away with it.
Okay.
Where do you happen to position yourself in this old debate? What came first, metabolism or codes?
Metabolism.
Metabolism.
Yes, of course.
So you are siding in with, say, Freeman Dyson, for example.
Sorry?
You are siding in with Freeman Dyson, for example, who posits that metabolism must be the starting
I'm not siding
point.
with Freeman Dyson. I
You're
think
not.
his books are now absolutely outdated. And the idea of having two origins of life, one with a code and one with metabolism, was nuts. So no, I am not a Freeman Dyson supporter for lots of different reasons, but definitely not. We automatically, any system that is far from equilibrium has information in it. Automatically, the information in the cyclone. It's not a coded information, but it's information. The molecules in the cyclone know what to do next. They can't help it. Okay, they're pulled in. So that's information. And information gets more and more subtle, of course. And, and it's a whole other kind of course to talk about the origin of information at the coding level. But I'll just say something about this mineral green rust, which is, I'm sorry I never got around to showing you this. But here's, in green rust, basically you're looking at layered mineral. There's ferric iron and ferrous iron and red and green, okay? But some of those greens could be magnesium. Okay? Now the magnesium doesn't change into redox state, so the magnesium is there. If you oxidize white rust to green rust and then keep oxidizing it, the magnesium always stays in the same place. And then you reduce it, it stays in the same place. It's kind of information. I mean, it's not terrific, not that helpful, but it means that the system has a memory right there, in spite of the redox changes round about it. So, this is a very kind of humble way of thinking about the code, but I think that's, the RNA world is not humble. They are very pleased with themselves, and they never worry about the initial conditions. They never worry about where the million electrons a second come from for the billions of RNAs and DNAs they've got to deal with. So, I'm fiercely opposed to the RNA world as an origin of life. It's, you can call that an origin of life because it would be an origin of life. But life emerged. It does it in very small steps. I said yesterday, somebody showed me the aeroplane from Brazil that first got to Paris, I understand, and that was about 120 years ago, or 130 years ago. And now we've got jet engines to go to Paris. But if you actually follow an aeronautical engineer, they were very, very small steps. And every now and then, as we know, unfortunately, one of them was rejected because it's the law of natural rejection. Mostly everything gets rejected. Only very few survivors.
Michael, posso fazer uma pergunta? I would like to ask something. When I entered the chemistry university, I had like a lesson about this, and I was could you talk about the coacervate hypothesis and
The what?
Coacervate? I remember they calling it coacervado.
Look, I can talk about it, but I want to talk about it my way. Okay?
All right, in the prebiotic soup.
In 1867, I think, or 77, Karl Marx wrote a letter to one of his friends, about what was happening in the markets and so on. But his first paragraph was about the emergence of life in this letter. I could send it to you if you like. It's an incredible letter. Marx, whatever we think of him, he was a Victorian intellectual. He was keeping up with the science all the time. And what he knew were people like Pfeffer and Traub in the 1880s were making membranes of inorganic material and suggesting life started that way. This was picked up by people like Leduc and Mayakovsky. So the whole consideration of before the First World War was that life started inorganically. The opposition was Pasteur's acolytes. Now Pasteur, as you know, said you cannot have spontaneous origin. But he was talking about organics. And even Pasteur changed his mind. But the terrible, awful psychological thing that happened was that the people who took over, all the acolytes, all the research students of Pasteur were adamant that you could not have spontaneous generation. So anybody who talked about spontaneous generation from inorganic molecules was laughable. In fact, the first great book on the mechanism, notice the title, The Mechanism of Life, was by Leduc. And he had to publish in English because they wouldn't let him publish in French because they thought it was nonsense. That book is still a beautiful, beautiful book to read. It's called The Mechanism of Life by Leduc. Then came this devastating First World War, which killed off a huge amount of intellectual science, killed a lot of German science off. What did it leave? It left basically a kind of you could call it a Marxist-Leninism, I guess. And Marxist-Leninism then became the structure of scientific socialism. So we're going to be scientists now, and we're all on the left, so let's think about how we can start life. Well, it has to be egalitarian. So let's have organic molecules raining from space and making little coacervates, little organic pods. And let's have UV radiation come down and turn that material into life. And that's great. And Stalin thought it was wonderful, and they gave him the prize. And Oparin, who, by the way, is the author of this work in 1922 originally, was the supporter of Lysenko, who led to 20 million deaths of starvation, because he said that Lysenko said you could take the... What's everybody talking about? I'm sorry, I'm going to talk about this because we've realized the political influence in psychology on how we think, and we've got to think for ourselves. So what happened was the Ukrainians, of course, had lots of wheat fields, so Lysenko said, well, let's just take the wheat from the wheat fields and put it in Siberia, but make it cold first so it gets used to the climate, and then we can grow Ukrainian wheat in Siberia. And then, of course, we can put the Ukrainians there as well. That makes real good sense. No, this coacervate hypothesis is absolutely appalling hypothesis. It's got nothing to say for itself. And it was taken to Southern California, and they picked up on it, for goodness sake, because Miller had made amino acids from methane, ammonia, and sulfuric acid. Well, of course, all that told us was that it was easy to make amino acids. But we're suffering from those experiments and those ideas to this day. They are ludicrous. I want to say it, they're just silly. They're not worth arguing, as I haven't, I admit. I don't mind arguing about all kinds of things, but not about that. They were politically motivated ideas. And I don't want the Stalin Prize, and I certainly don't want the Aparin Prize.
Okay, thanks. I would like if you could send me the text you talked about.
Sure.
Marx.
Sure. It's delightful.
Any more questions? No? Okay. Thank you. Thank you very much, Professor. Please. Não, tá, pode deixar. Okay, let's continue. I will introduce myself. As I said before, my name is Dimazai. I am from Londrina State University. My talk today will be about minerals and the prebiotic chemistry. According to Bernal, minerals could play the following roles: concentrate molecules from dilute solutions, protect molecules against degradation from UV radiation and hydrolysis, and catalyze organic reactions, and work as a primitive genetic code. There are several papers showing that at least the three first are possible. However, we must remember that minerals are complex compounds. My talk today will be about the following topics: minerals absorb more charged molecules than uncharged molecules, suggestion of prebiotic seawater, the period of time in prebiotic chemistry experiments, and the strong adsorption of molecules on minerals, and the complex mixture of organic molecules. What I am going to do is share my doubts about these topics, okay? If molecules were diluted in the seas of prebiotic earth, preconcentration was the first step for all other processes of molecular evolution. As I said before, minerals absorb more charged molecules than uncharged. Modern proteins are made up 75% of amino acids with uncharged R groups and 25% of amino acids with charged R groups. However, minerals absorb much more amino acids with charged R groups. The following questions should be asked. What were the mechanisms to produce peptides and proteins with more amino acids with uncharged groups than charged groups? Should we expect the composition of amino acids adsorbed on minerals to reflect the present-day proteins? Was the adsorption of amino acids on mineral important for the origin of life? Could mineral play a role of cleaners of charged molecules? What this could mean? Maybe minerals adsorb charged molecules, leaving uncharged molecules to interact with no-polar molecules to form micelles. Okay? I don't know. Most of the experiments involving adsorption, protection, and polymerization of molecules were performed in distilled water or sodium chloride solutions. However, distilled water or sodium chloride solution could be not considered a representative of the primitive oceans. So, what was the composition of cations and anions of prebiotic seawater? Izawa performed sequential leaching of the meteorite sample from Tagish Lake. Based in the work of Izawa, we suggest an artificial seawater that we named it as a 4.0 seawater. Unlike today's seawater that has high concentration of sodium and chloride, we see here the high concentration of sodium chloride. Our seawater has high concentration of magnesium and sulfate. Okay. That is the difference, this seawater. Okay. We tested this seawater in several experiments of adsorption, and one of these experiments that showed that this seawater did not decrease the D001 of the montimorolonite. This is important for adsorption process. Another topic is the period of time of the prebiotic experiments. Probably the longest prebiotic experiment ever performed was carried out by Miller groups. Took 27 years. I don't think these experiments could use it for a PhD student. They prepared a solution of ammonium cyanide, keep it at minus 78 degrees, and after 27 years, they observed several nucleic acid bases. Okay, we can see a picture. They synthesize also amino acids. Okay. Before I came here, I asked one of my students to prepare a solution of adenine in distilled water and the other in this water that we are using. I have to point out that the experiments of prebiotic chemistry, the adsorption, usually they do up 24 hours. Why? Because most of the adsorption after 13 minutes, 10 minutes, it's a very fast process, okay? So, the adsorption was followed for 21 days, okay? In the first week, the adsorption did not change. We have about 13% of adsorption of adenine. So, after 1 week, the adsorption continued, the material continued, absorbed the adenine, and after 3 weeks, we have 100%. What I am telling this example shows that the results obtained from prebiotic chemistry experiments should be interpreted with caution because of this factor, the time. Okay? Another question. The interaction between peptides and the mineral increases with increase the size of peptides. Peptides longer than 7 MER could be irreversible adsorbed on hydroxyapatite. Also, I have other examples. Adenine, okay, adsorbed strongly on montimorolonite, and it could be desorbed from it only by high concentrations of hydroxy. Okay, the molecule adsorbed, you cannot take out from the mineral. Another example is from Lambert group, aspartic acid, was not desorbed from silicon dioxide by acetonitrile plus water. So, we should ask the following questions. Maybe strongly adsorbed molecules will be not available for any further reaction. What does this mean? Maybe adsorption is a dead end for hypothesis of emergence of life, origins of life. Okay? Also, it could be argued that sometimes immobilization is required for reactions to take place. Maybe. We do not have results about this. I will cite only one example. In the work from Lambert, they observed that on a decrease of reactivity of glycine for the formation of the peptides when glycine was served in the interlayer clays. So we always read, minerals can catalyze reactions, blah, 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 but this is not true always. We have to remember this. Another problem. The complex mixture of molecules, organic molecules. It's well known that hydrocyanic acid chemistry produces a wide variety of compounds. However, the yield usually is very low. Example for adenine synthase. The yield does not exceed 0.10%. Another problem with this chemistry is that you have to use high concentration of these acids. This is another problem. Another well-known reaction is formaldehyde condensation that also produces a mixture of riboses. About more complex mixtures. If you look at the relative abundance of amino acids obtained from experiment using exogenous sources, ICM, meteorite analysis, you can see that it is a complex mixture. We have a lot of amino acids. Also, the same is true of the relative abundance of amino acids obtained from experiment simulating sources from the Earth, atmospheric, hydrothermal, other environments. Here, I would like to point out the following. If you see the mixture of amino acids from endogenous sources is closer for the composition of amino acids of proteins of living beings of the Earth. What I am telling this, the sources of producing amino acids produce more amino acids that we have in our proteins than exogenous sources. We have a lot in the first line, a lot of amino acids that are not protein amino acids. So we could ask, maybe we are from Earth mesmo, maybe, same, okay? Another complex mixture organics, the analysis of emissions on meteorites show a complex mixture. We can see here, they detected 74 different amino acids, But in that, the mixture is more complex in this table because 70% of the carbonaceous meteorites are unidentified compounds. Okay? So the question is, could minerals from a complex mixture compound select the right ones? My question is, maybe this the emergence of life could be we could see this way, the life could be originate in this kind of thinking. We have to think about this, okay? Well, there are a few experiments showing that minerals could choose some kinds of molecules. As an example, an experiment carried out by Lambert Group showed that when amino acid plus silicates were mixed, occurred the formation de DKP, means dead end. Okay, always when you hit the amino acid and form DKP, it's dead end. However, when glutamic acid plus leucine plus silicate were mixed, the linear peptides of hexamer were obtained. And it is very interesting that the peptides were not random, okay? They obtained some sequences. Well, in conclusion, after almost 70 years of Bernal books, the role played by minerals on the origin of life is still unknown. And I would like to say a last phrase: the origin of life cannot be discovered, it has to be reinvented. I would like to thank the people that collaborate with me, Dr. Alexandre Urbano, Andrea Paisano, Dr. Costa, Dr. Cássia Thais, my wife, Christine, and Eduardo de Mauro, and Maria Colin Garcia. Also, I have graduate students, PhD student, Rafael Rodrigo, master students, Bruno, Giulio, and Marcello, and the undergraduate student, Bruno, Fernanda, Júlio, Rafaela, and Lorena. These are parts. We like parts. We are lazy. Here are some sites, my lab, the Society Astrobiology, and the Rede Brasileira. And thank you very much. I want to share my doubts about this way to think about the origin of life. That was my plan today.
Hi, Dimas. Thank you for the talk. Do you think that specifics about the minerals in the early Earth could have contributed to the selection of particular amino acids? Do you think there might be a link between the, say, 20 or so amino acids that Earth life uses and details about the chemistry and minerals in the early Earth?
Okay, there is a problem with minerals because minerals they like zeolites no, but usually minerals like charged molecules. So, and the most produced amino acids, glycine and the alanine, they are not charged as aspartic acid, glutamic acid, lysine. Okay, so we have another problem. I can answer because we have a lot of dates. Only one mineral, montmorillonite. 90% of the articles about adsorption, think about prebiotic chemistry, use this only one mineral. Okay, it's possible, but I don't know.
But why are people only using this mineral?
Because it adsorbs. It's easy.
Is it the only one that does the trick?
Yes, it's a trick because if you took example, you took magnetite, okay, it's a prebiotic mineral, exists, okay. It is not the adsorption is not easy. The molecules on this mineral, but if you take gray the professor talk, probably adsorption will be very high. Okay, that is the problem because adsorbs. Okay.
Thank you very much for your presentation. I am not the field, I don't work in the field, but one thing, I work with biochemistry, and one of the most important anions in biochemistry, in metabolism, is phosphate, okay?
Oui.
Several years ago, there was a paper of Westheimer saying, whose title was, Why Nature Chooses Phosphates. And more recently, another paper, the title was, Why Nature Really Chooses Phosphates, okay? Because it's central in all metabolism. And I don't see phosphates in nowhere. Why nobody choose phosphates to study the effect of this anion, important anion, on prebiotic life? I don't understand why.
Yes, also, I try to work with phosphate, okay? But the problem is the phosphate is not a soluble. Major phosphate that we have is in the form of the calcium phosphate. Okay, so the calcium phosphate, that is not the, so this is one problem. How the nature chooses phosphate, I don't know. But is a problem for prebiotic chemistry. There is a meteor, I think 5-6 years ago, an article about a soluble form of phosphate. Okay, but the phosphate was in seawater. We have calcium, we have magnesium. Okay, I tried some experiments in my lab using phosphate, but always is not easy. The problem is in clay minerals such as Montemorolonite, we have to work in very acidic pH for adsorption occur. Okay, but it's a good question. Phosphate, nitrate is no one work with these small onions.
Okay.
Yes.
Okay, I'm trying to figure, Lia Amaral from the Physics Institute. I'm trying to figure out the similarities and differences between the two approaches I have heard. It seems to me that your approach is more equilibrium-like, while his approach is very dynamic and out of equilibrium in a sense. And I would like to ask you whether it is really this the basic point, or if you see some other basic differences between the two approaches.
My approach is this. If we have a really junk of molecules that time, because we have molecules being synthesized in hydrothermal vents, okay, a lot more than today, probably. Okay, we have molecules comes from meteorites. We have all molecules. We have this system with a lot of molecules. It's not in equilibrium, my system. It's far from equilibrium because adsorption occurs because there is a no equilibrium. So what I am trying to figure out, if it's possible, think the origin of your life this way. Is a way you think about the increase of complexation. Adsorption is the first step. If adsorption did not occur, if we can figure out how to take some molecules to do, this approach is not right. The book of Bernal wrote 70 years ago, okay, is a very good book to read, but maybe these ideas is not okay, are not okay.
Well, if you don't mind me answering joining in this last question, I would always say you've got to get the physics right first. So have we got the physics right? Well, what the physics would say is that for breakfast, you had all kinds of different things for breakfast, but actually, in terms of amino acids and DNA and so forth, they were all very, very similar, and sugars, of course. In other words, you had a very low entropy breakfast. Now, you could have taken coal and stuff from the rubbish dump and so forth and put it on your plate, and you know that you wouldn't have eaten it because it was high entropy. It was a mess already. The problem with delivering, to my mind, material from you can have lots and lots of organic molecules, no question, coming in from space, but they're just there, and they're high entropy start. Now, anything that anything does in the universe has to, paradoxically, have a relatively low entropy. Now, you could say that I'm arguing that, well, but the universe makes plates, it breaks plates, it kind of makes a mess. Well, a good example of how it works, I think, is you think of the cow in the field, and it's eating grass, okay, and it's generating milk and so forth. We drink the milk. But actually, as I would say, what really happens to the cow is it makes a cow pat or a cow pizza or whatever you want to call it. Now that is very high entropy for the cow. It doesn't want to look at it anymore. But for the horsefly and the cowfly, it's a perfect pizza. It's low entropy for that structure, and so on, and for the bacteria thereafter. So in other words, I would argue that from the physics point of view, you have to start with a relatively low entropy system. And the good thing about a hydrothermal vent is that it's very well focused, and it's giving you particular molecules, like methane and hydrogen, all the time, for, as I like to say, for 10 to the 21 nanoseconds. It's ever coming. You don't run out. You never run out of food at a hydrothermal vent. But you're going to run out of meteorites.
More questions? Okay, thank you very much. Now we will have the third talk from Dr. Teresa Souza. Dr. Teresa Souza is a collaborator from Luigi at Rome. In 2001, Dr. Teresa acquired her degree in maths at UNESCO, and in 2006, her PhD in biochemistry, Instituto de Chemistry of USP. Since 2007, she has been developing, studying construction of a minimal cell, interface, physical chemical field activity, origin of life, vesicles, liposomes, synthetic biology, minimal cell, protein synthesis, Poisson Boltzmann, micelles, membranes, electrolyte interaction, membrane protein interaction. Dr. Souza published several works in book chapters related to today's talk theme. Please, thank you very much.
Hi, I am Teresa, and I give the talk a little bit different from everybody. I will concentrate in just a small subject and something that makes me shake to hold the microphone. To concentrate in a small part of the work that we have done together with Luigi. I'm very interested in more in the physics of how things work than in the chemistry, despite the fact that I'm a biochemistry. And I will try to talk a little bit about compartments in general, but a very, very subtle touch, right? It's okay. So let's talk about compartmentalization, specifically in vesicles in origin of life. Professor Russell, I want to come out of here alive, please. So jokes aside, why I choose vesicles? because modern cells are composed by lipids or phospholipids. It's just 28%. All the rest are different kind of proteins that are channels, that are structural, that's outside and inside, it's just one side, and make all different sort of things. But those are modern cells. Most of the work that I have done was with binary mixtures of lipids and phospholipids. Why? Because lipids and phospholipids in several proportions and mixtures would be difficult to lead and to treat as a biophysical research or a biochemistry or physical chemistry properties, just for that reason. So we minimize as much as we could. I will not take the human being as a model, but I will take the Cedrus libani. That's a wonderful tree that can reach up to 40 meters in the heights of Lebanon. If you take this tree, that's what human being can do very well, and you start to deconstruct, and you come to the leaves, and you see, you cut one of these leaves, and you go to the microscope, you can see a conglomerate of cells. And if you look to this very modern cell, you see that's extremely compartmentalized. You have the nucleus, you have a vacuole, you have some chloroplast, you have a wall that's composed of cellulose. And if you take each one of these pieces, you can go all the time further down. And you can come, say, I'll take the nucleus, it's made of chromatin, chromatin is made of DNA, DNA are made of nucleotides, membrane. You can have the proteins in the membrane, they have amino acid, the phospholipids and lipids, and you have the different kind of them. And if you come to the cell wall, it's made of celluloses, celluloses are made of sugar. But basically all the life that we know today, that's basically living cells, they're composed of more or less the same kind of building blocks. How these building blocks originated, I don't know. Most likely in thermal vents. And it's almost a consensus, and it's, in my opinion, a very valid and approved way of life evolving. It could have been one way, many ways that life evolved, I don't know. We in the group of Professor Luisi, we always say origins of life, okay? We are not touching in the very bottom. We touch in the point that this substance already existed and how the substance could interact with each other. In the very early beginning, I don't believe that very large molecules of phospholipids were present. But the molecules that were present, they could gather together and form some kind of structure that most likely were not very stable and most likely needed a huge amount of material to make a structure, to make a compartment from this molecule. But very short molecules and fatty acids, for instance, from 4 to 12 carbons, when they come together, they can stabilize themselves and form compartments. They're stable? No, they're not stable. Modern cells are much more stable, but they are much more stable because they are much more complex. But in any case, what a compartment does is to separate internal from external environment. It could be anything. It could be, as in the past has been studied, conservates that has some problems when you think about separating outside from inside. They leak. So whatever you put inside, it can very easily go outside. If I forget about Oparin and I take Stephen Mann, now in England, he has coated his coacervates with some sort of lipids, and it makes them more stable and less leaky. If you go to other compartments and you are interested in see clay, Montmorillonite surfaces and compartments, you please take a look in Martin Heskey, Protocells 2007. There are many more reviews, but this one, it's written in a language that I can understand and I believe that everybody else can. And it's a very light way of putting this. So if you think about lipid vesicles, you take about Luisi, Dimmer, Morowitz, Solstak, and so on and so forth. David Dimmer, it's a very special person in this field because he basically starts to produce vesicles from fatty acids from extracts from a meteorite. And from there, we bought the idea that maybe these molecules could come from the universe. I ask you forgive, but it's the field. It has come from the universe and it has been produced in the thermal vents and so on and so forth, and then we could build these early compartments. Although they were not stable, although they were not perfect, maybe these limping compartments could have helped what we know today as life. So this is a figure that I got from one of the papers from Peter Walden and Pierre Lemonard. It's written in Life in 2015. And it gives us what they believe from literature that has occurred from the formation of Earth more or less 4.5, 10 to the 9 years ago to the first appearing cells in 3.5, 10 to the 9 years ago. In this time, this first cell sometimes is disputed because they say, oh, maybe this is a contamination, it's a present-day material that you found there and whatever. I will not come to this discussion because I don't know. I have never seen these organisms by themselves. I have never studied them. But anyway, I'm very much interested in non-living form of matter in prebiological, what they call of the complex protocell. And how things evolve up to there, I don't know. Okay? So I'm sorry, if you're interested in read this paper, that's the reference. It's a very nice paper. Why I want to study compartments and why this is important, whatever kind of compartment you have, it's a mineral surface, it's a solid surface, it's atmospheric aerosol, it's water droplets involved by oil, whatever it is, it can separate the outside from inside. That's the most important thing. It can have some permeability that lets you to throw out what it's not anymore useful for you, that's waste, and capture from the environment what is necessary that you can build up your metabolism. When I work with amphiphiles, they can self-assembly. They can entrap solid, and they can make a very distinct internal medium from external medium. Whatever else you put it together with these phospholipids, most of the time, if you search for stabilization, you can make more stabilize the membrane, you can increase the permeability, or you can decrease the permeability. So whatever you mix with them, or whatever is the proportion between each one of these different kind of lipids and phospholipids, you can tune how your membrane, how your barrier will work. That's our interest. One of the interesting things in these kind of phospholipids is that Professor Luisi had a long time ago proposed that these vesicles can per se grow and divide without any information from DNA or RNA. So if you start to put material in the medium, they will capture this material, and these structures will grow, and in a moment it will get unstable because it grows too much and will divide in different molecules. This is a work from Pasquale Stano, and these are freeze fractures from different vesicles that he believes that is dividing. But the main idea here, and the only thing that I want to tell, if you add lipids to a phospholipid vesicle, it may lead to splitting. And you have a generation that's mother and a generation that's daughter. This was one of the ideas that motivate them to start the search for the first way to make a system that was able to capture something inside, make a reaction, and start to split. So if you take the idea from Bartel, Shostak, and Luisi about a ribozyme minimal cell, you would have an environment that you had lipids or whatever sort of building block that will constitute a barrier. It will enclose inside the material that were necessary to replicate itself. And in a certain moment, this mother would grow and it would divide. So you need to grow the membrane, and you need to divide all the material inside that's making the metabolism. What they try to do in minimal cell, protocell, is to construct something that's able of Darwinian evolution in somehow. It means it's able to sustain itself, to build itself. It's able to grow and divide, and it's able to evolve. But it was too far from my knowledge in chemistry to help in a more effective way. I could just produce some green fluorescent protein in a very small size, lipid vesicle, and then I start to get very puzzled with the following. When they do this minimal cell, they in general use a pure system. Pure system is a extract from bacteria, from E. coli, that has been purified, and the guys in Japan know exactly what kind of components they have inside. They have the machinery for take the RNA or DNA and make the proteins. So they know each one of the 82 components inside. When I have done this experiment with green fluorescent protein, I saw that these very small vesicles with 200 nanometers of diameter was able to produce green fluorescent protein. It means that to produce something, it was necessary to entrap at least one of each one of these components inside. Because if any of them were missing, it would be not able to produce the protein. So how it would work? What was the statistics of entrapment inside? Would just the membrane be something very passive, like a bag? So, let's throw in this bag. Or would this membrane be an active role in making this protein, in helping this to happen? So everyone that works in Origins of Life sometimes thought about this. And if you take a basic chemistry law, to a reaction occur, two of the reactants, or how many reactants we have, they need to come close together, that they can see each other, that they can interact. When you put a compartment, when you compartmentalize, you reduce the volume, and you make higher the probability that one see on another. So if you have two components in an ocean, and they are floating around, the probability that they will meet each other is very low. But if you take the same two components and put in 1 microliter, this probability gets very high. So membrane would not just be the bag that's holding this together, but it's also a facilitator. It could help that the reaction would occur, as many people has proved before. And if you take papers and you take studies from people that's outside of our field of Origins of Life, for instance, Professor Yolanda and Professor Hernan Shaimovitz, they speak about reactivity of membranes in micelles and how these help chemical reactions to occur. So membranes are much more than just bags. And then we come to, I think that our colleague made this question, but it was a different question, was if RNA or the metabolism come first. So we would ask the question, before the last common ancestor was simple primitive cells, but how these primitive cells arrived? Was the biochemical network developed inside the compartments, or the biochemical network was developed outside of the compartments? What do you guys think about this? Can someone give me an opinion?
I don't like the word network. It means basically cycles and pathways. Like we've got cycles and pathways, not networks, I would say. Networks gives a false assumption about how life works.
He gave could you everybody understand? He said that network does not give a very precise idea what happened. It try to force you to a leading way, right? That life appeared or something.
Life is about pathways and cycles, not networks per se. So you've got, so in other words, this evolution of the pathways as it goes. It's not just things interacting like this. They're making things through engines. So I think that we have to be very careful with language. So you might have thought I was over political when I was talking. What I want to emphasize is that, I have the unfortunate advantage, or I have the advantage of having been raised in England. So I'm English. So but I have English on my mind when I think about things like the law of natural selection. It's a bad term because the expectation is selection. Actually, the expectation should be rejection, including scientific hypotheses. Most scientific hypotheses have been rejected. The survivors are okay. And so it gives us a bad view of how our life's going to be, because we're always going to be looking for selection, and therefore, who's selectable, for example. So network is an old idea by Kaufman and so on. They don't deal with electrons. They don't deal with what life actually does, ever. They just wonder how it started and how did we come to be. It's an emergent structure from a low entropy feed.
No, pode. Please. No, go ahead. We can, right, Douglas?
No, perhaps better is if you go.
Go ahead.
Yes,
Yeah.
okay. When I have been studying biomembranes, I have focused a specific phospholipid.
Okay.
I was attracted to this one because I had the idea that could have something with the origin of life. I never wrote this in my papers, but the point is that I focused on DMPG. And DMPG is very particular. It does not appear in eukaryotic cells because it has a very particular property that I have studied in detail. It forms spores. It forms spores in the membrane, and they are switched by temperature. So you open and you close by temperature in a phase transition, a physical phase transition. And just because of this, it's very bad for eukaryotic cells. And it has some charge. And so this particular phospholipid does not exist in eukaryotic cells because it would induce instability. But I think it might be very important for the reasonings regarding origin of life. And I wonder whether this is a crazy idea or it has some meaning.
Okay.
Is it rude to say something to that?
No, please.
So remembering that it's the law of natural rejection and making an analogy with, shall we say, hunter-gatherer society. There are no bureaucrats in hunter-gatherer society. There was nothing that was wasted. As soon as the kid's 4 years old, he's doing something. What would the lipid be doing at the emergence of life? It doesn't do anything except it just is a bulwark. That's all. It doesn't do a job, a real job. It doesn't do a metabolic job. So why would it survive? Surely it's something that's invented by metabolism because it needs to find a barrier, which is a very limited, by the way, barrier. I mean, mostly it's protein.
That's a very, in the other side of the force, it's a very interesting idea about this lipid, that it can be forming pores. Because we are, in the field, we are very thrilled when we could use alpha-hemolysin, that's a protein, to make the reactions inside of this chemotron or protocell or whatever, minimal cell project to work. So when, I forgot his name, Noro could do it, he used this alpha-hemolysin to permit, to allow that material was internalized by the membrane and it could keep the reaction going for 100 hours. It was like thrilling. So imagine that we can use this lipid that has this property. It's less like modern and it's more like less protein-y. So most of the time we are trying to go out of proteins because proteins are too complex. So once that this molecule exists and that has this property, that's a thermal property of forming domains, and these domains lead to a pore formation, if the pore is large enough that can allow something to permeate easily, it's a very valid idea and it's a very worth idea. So this is my point of view. So then we come to this question, and I don't know if I could answer this question or not. It's outside or inside. So we draw an experiment, and before coming to the experiment, what we know about the physics of solute entrapment. So we know that when lipid vesicles they are formed, they can entrap things. They can entrap things inside of the aqueous nucleus, and it can entrap in the membrane. It's used by all the time by drug delivery, right? And especially for small, very small molecules, they are all the time used in drug delivery. The other thing, we have an overall entrapment, but we never, a few times we have studied vesicle by vesicle to see how it entrap. And that was our question, like, it's everyone entrapping an average number, or is specifically a huge amount being concentrated in some and the other not? Because if everyone is more or less entrapping 2 or 3 molecules, so this will be a passive bag and we are not interested. But if something different would happen, then we would be very interested in this. Maybe we could start to think about where the reactions started to be entrapped as a metabolism. So what we did, we take, first of all, what we had in hands, that was a pure system, that are different molecules that look like here in the representation of dog food, and we throw lipids together, but a mixture of lipids that allow the formation mainly of equally small-sized vesicles and unilamellar. That was important to us, because if it was multilamellar, we could not make the calculations correctly. It would be a rough approximation.
Teresa,
yes.
Please, we have almost time. Okay, thank you.
So this was the idea behind, and then we clean outside, and what we have, the expected for the entrapment would be like 3 molecules inside of vesicles. But if you take this picture, that was, we counted like 7,700 to 10,000 different vesicles in many days, different experiments and months. And what we see is this. Same size of vesicles, they have entrapped a different amount. The numbers inside is how many molecules of a protein called ferritin is inside. It's clearly not a Poisson distribution of entrapment. These two have the same size. One has a huge amount inside, the other one is empty. Most of the population of vesicles was composed in this way, like same-sized, but they were not entrapped in many, and just in few. And the few that had a lot. So the concentration, when you added, was 4 millimolar, but when you count what was inside, was like if you put 34. If you put 8 in the beginning, you count in the end like 30. And so on and so forth. So when you add the lipids to that, it had locally increased the concentration. But then you can ask me, okay, Teresa, they are increasing the concentration because it's protein like the membrane, and then they are connecting to the membrane. This is a picture that shows that they are not connected in the membrane in any way. So they are dispersed, equally dispersed. They don't have a preference to be in the membrane. So this is the protein. If I take what's the name of this? A ribosome. We see that's really entrapped inside of the vesicle, but outside we don't have many of them. And if you see the picture again, they are not connected to the membrane, but they are highly entrapped inside of some vesicles. So this follows a power law. When this particular event of finding very filled vesicles occur, but it's not many of them that are filled. Okay? Power law is quite common in nature, in the living process. So Luisi was very proud of this and called this overcrowding. That again, it's a misnaming, but whatever, he gave this name, what can I do? So if you see the packing limit, the ones that are very concentrated has like 18%, 14%, or 2%. 2% of the packing will be 70 and so on and so forth inside. And the frequency, small vesicles had the power to concentrate more than the larger one. So the gray values show where it has been filled, and the white one is the one that are normally filled. So we proposed an idea how it would happen, and we thought that a small one could concentrate more, because in the process of closing, they would have some cooperativity. So once that one molecule was inside, it would make the lipid cake slower to close, and so on and so forth. That's not a good model, but was what will come in the time. So if interests someone and someone could shed an idea, it would be nice. Then they repeat the experiment with dispersed or diluted solution. And again, we could see the production of green fluorescent protein in a very diluted system when we add molecules of lipid, and not when it was just pure cis diluted in water. So that's what I want to show. And this is a joke, but it's not a joke, it's very serious. So, todo mundo pode ter o que você tem, mas o que você é, ninguém pode ser. So we keep doing, no matter what. Thank you very much. I'm sorry if I was running.
Thank you very much. I would like to say thank you for Dr. Russell, Teresa, and for everyone be here. Now we will have 10 minutes for a breakfast, okay? After we come back. Thank you.
Hello, everyone. Let's start the next topic, geologic perspective and first trace of life. My name is Flávia Calefo. I am a researcher at Brazilian Synchrotron Light Laboratory at Campinas, and I will present you the next speakers. Since the Earth was capable to have suitable conditions to shelter life, as we know, we have preserved in geological record trace of life, which can be biomarkers, chemical fossils, or microfossils. And the geological record can tell us a lot about the early life on Earth. This topic aims to bring the discussion about what the geological record can tell us about the origin and evolution of life. And the presentations here is based basically in what we have in the geological record, especially in the Archean, when we have the oldest signs of life found until now. Our first speaker is Dr. Nora Nofke. She has a degree in geology and paleontology, master in geology and paleontology at the University of Tübingen, Germany, PhD in geomicrobiology at the University of Oldenburg, Germany. Nora has a large experience with the study of microbial fossils on geological record. She practically created the area of study of microbialites in clastic sediments, with the most important publications in MISS, microbial-induced sedimentary structures. She won the American Academy of Advanced Science Award in 2015. Nowadays, Nora is an associated professor at Old Dominion University, ODU, at Norfolk, Virginia, United States. And today she will present the talk, Old Fossils, Examples from Archean Rocks of South Africa. So, Dr. Nora Nofke.
Okay, thank you. I just have to find my talk. Yeah, if you just pulled it up. So I stay here so that everybody can see me. Thank you very much for inviting me to this wonderful workshop here. I'm always very happy to be here. It's my second visit, and it's just great. So thank you. And you folks don't fall asleep in those very comfortable couches there. So 4 screens, I try to maneuver that. That's my first talk. Like, I don't know where to look. Anyway, so old fossils, examples from Archean rocks of South Africa, and I call them old fossils because I think it's pretty silly, this race of who has the oldest fossil and the oldest, biggest fossil and all that. So for me, all the oldest fossils are old fossils. I'm getting old too and wise, as you can see. So now, what are sedimentary structures in really the oldest rocks? What are they in fact? If you think of evolution, we all know stromatolites. That's this one in the upper right corner. What are those structures? And in fact, they are nothing more than solid manifestations of biofilms. So the word microbiolite actually is nothing more than fossil biofilms. And it really depends on where the biofilm grew, what kind of environment, the positional environment, then we get different microbial fossils. And that's what I'm going to talk about today. So what you see here, just very quickly, the upper two photos on the left, that is a microbiological document of some sort of a biofilm. I don't know how they make that, but you see it has this kind of mushroom build-up, and on the right, that's a stromatolite. Looks very similar in a way. Then the second row, here we look down onto the surface of a microbial mat, which is for now an organic layer composed of trillions and trillions of microorganisms. And we see those very strange crests on the surface. Especially on the left, you see that a little bit better. And you get the impression those are like crests that define a honeycomb-like pattern. And it's not by accident. That's a pattern that forms by cell-cell communication, a little bit more about that later. So the microorganisms talk to each other and they decide to arrange in this surface pattern. In this case, it's a response to a stress factor like desiccation. So on the right, that's a modern microbial mat, and on the left, it's a very old fossil one, 3.48. That's actually from Western Australia. And then in the lower two photos, on the left, that is actually an experiment by Paul Studley, who works in health sciences. He is one of the first real biofilm researchers, one of the pioneers, and he showed that biofilms react to water crossing a sedimentary surface. The biofilms create certain shapes, and in this case looks like tiny mini ripples of sub-millimeter scale, but on the right you see the same stuff in the fossil record. That is a fossil sandstone surface. So those are manifestations of biofilms. And those are actually the oldest fossils, so things like that. So let's forget about stromatolites for the moment. I hope there is no stromatolite friend in here who feels now offended. I like to focus on a little bit different biofilm structures, which are microbially induced sedimentary structures. Those occur in clastic sediments, like sand, not so much mud, depending on what you're looking for, carbonate sand, things like this. So loose material, not real, where stromatolites grow. So you do not have rapid mineralization processes in a setting like this. So you see two photos here on the right. Yes. On the right, so those are multi-directed ripple marks here. That's one and the same surface, and you see the ripple marks are arranged in patches, and the patches show different directions. Those patches that have a ripple mark direction this way, so for everybody, this way, here, a microbial mat is growing in the sediment. It's an endobenthic microbial mat that holds the sediment grains in place. So that's an older generation of ripple marks. On the right side, there is a fossil example of erosional remnants and pockets. You see a planar part of the surface here. you all know geology, I hope, right? So this is a rock bed that was tilted tectonically. That's why it's a little bit like this. So this is the fossil microbial mat here, this planar part, and erosion has formed those depressions that you see, which show ripple marks. That's the sand beneath the microbial mat. Here just another example. This is a rock very old. I think this is from Neoproterozoic, something from Australia, but there are just some cracks and crinkles in there, and in the lower right you see a modern example, so that is a fossil biofilm right there. One most popular MISS are wrinkle structures, which are not very attractive, and but that's one which is very, very common, and I think one of the most described MISS in the fossil record. So microbially induced sedimentary structures are abbreviated as MISS for those who were not at my talk yesterday. So let's take a closer look at the formation of those structures in clastic settings. So clastic sedimentary systems are governed by erosion, deposition, and deformation. And so if we take a look at this photo here, we think first, well, you know, those are sand grains and nothing more than sand grains, and they're just being moved around by waves and currents. But that's not the case. If we take a closer look, we see that there are a lot of microorganisms attached to the grains. And the lab rats, so to speak, of people like me, who are geologists, and they look for microbial life in oldest rocks. The lab rats are cyanobacteria. They are big, we can see them, so that makes life much easier. And here just two ecotypes that occur worldwide, Microcoelius tonoplastis, and the other one, Merismopedia punctata. So the Merismopedia punctata is a coccoid one, and Microcoelius tonoplastis is a filamentous one. And actually, if you read in the geological literature the word algal mat, that word derives from the cyanobacteria, especially Microcoelius, because people formerly believed those are blue-green algae, so like algae in a sense of plants, until in 76, Stenier found out, no, those are real bacteria. Anyway, so they're photoautotroph. So initially, microorganisms, when they start to colonize a sediment, let's say in a marine setting, they attach solidly to a solid surface like a sedimentary grain, which you can see here on the left. This is the surface of a sedimentary grain, and the microbes start to secrete its extracellular polymeric substances, EPS. They serve a various purposes. I mentioned that yesterday. Those are mucilages. They serve to transport nutrients, to protect the cell against any environmental factor like rapid changes in salinity, desiccation, and so forth. They serve communication. So those are the EPS, and they also assist the cell to attach themselves firmly to any surface. And as you remember, any surface on Earth, no matter what it is, wherever there is a few water molecules, there is a biofilm. It just comes together. You cannot clean a surface completely to get rid of biofilms. Almost impossible. Big problem for NASA when they send instruments to other planets. The instruments are contaminated, and let's hope that cosmic radiation takes care of that. I mean, but hopefully. Anyway, so that is the first step, how microbes colonize a setting in a natural sediment. So they form biofilms. And what is a biofilm? Michael mentioned this morning a little bit before. So first, there are, so in this upper sketch, you see little cells, whatever, microbes, floating in the water, close to the sedimentary surface, and whenever there is a trigger of some kind, let's say a source of nutrients, a foul fish or something like that on the ground, then the microbes move towards that source of attractiveness, and they start to form a biofilm. And what does that mean? The cells communicate with each other via cell-cell communication with electric pulses and chemical messenger molecules and so forth. What they really do is they tell each other, you go there, I go here, you go over there, and we all work together to get, as a cooperative, to the food source. And I cut out this piece and hand it over to you from everything that I don't like to eat, and so forth and so forth. It's a perfect bioreactor that is establishing, that uses an energy source. So here a biofilm starts to grow. There's a lot of EPS involved. They need to be firmly attached. And then finally, if this thing starts to grow and grow and grow, and there's a lot of cyanobacteria that join the community, which are photoautotroph, you get a several square kilometers wide biofilm, which we call a microbial mat. So a microbial mat is nothing more than a gigantic biofilm, one of the biggest organisms on Earth, I would say. And in the end, when the nutrient source is exploited, the cells disperse again and go to the next area. So biofilms are transient. They rarely ever exist for a long time. So this here is a biofilm in a natural setting. It's a microbial mat that covers a tidal flat, and if you think you don't see the microbial mat, you do, because you don't see the sediment anymore. Everything you see here on this photo, the surface, it's all microbial mat. You can walk here for hours, you never step off the microbial mat. That's how big that is. So it's a biofilm, big one. And those are also the oldest organisms we are able to find in the fossil record. So anything older, there is no geological record, and that's important to keep in mind. So we really cannot prove visually by finding a fossil about anything related to the origin of life. The rocks are not there anymore. That could do it, and if people try to find fossil in metamorphic rocks, don't believe them. You can't. You can't. It's gone. I mean, even the minerals are recrystallized completely. They're new minerals and so forth. There is no fossil in a metamorphic rock. So classic sedimentary systems, deposition, erosion takes place, but also time of quiescence. So nothing happens with the sediment, and that's then when the biofilms can establish, because they need a solid substrate, quiet, in order to very quickly form their biofilm. Biofilms can form within fractions of seconds, but of course a microbial mat takes months and months to develop. I talked about this yesterday, so I go through this here only very quickly. So we have in a classic setting, which is sand basically, moved around by water, by currents or waves, which is slightly different, doesn't matter right now. So we can have erosion of sediment, meaning sedimentary grains are being taken up by the water and moved, and then they are being deposited, which happens on the right side. If there is erosion going on, the EPS change the configuration within very fast, a blink of an eye, so that the biofilm, and with that also the sedimentary surface, is stabilized against erosion. So the sediment cannot be moved anyway. Then we have deposition, which is all the way on the right. So what happens is what happens when grains rain down onto a biofilm. Let's say, it doesn't matter what biofilm it is. The way the biofilm functions is mostly via a gradient. We've heard that this morning. A gradient So if sediment is being deposited, the gradient doesn't work anymore. The source of incoming light or whatever does not work anymore. The biofilm has to react. A microbial mat, which is photoautotroph, reacts, and the microbes give up their network that they have, their biofilm, and they start moving upward to the new sedimentary surface, or they walk, so to speak, with the migrating sedimentary surface laterally and try to escape this bombardment. And the grains that are settled down onto the microbial mat surface are being incorporated into the biofilm matrix. That's all that happens. And then there is, of course, the time where nothing happens in the center. That's when, I said it before, the biofilm is developing and becomes more and more complicated, and a microbial mat can grow. So those processes that I just mentioned, reaction to erosion by reducing the effects of waves and water onto the sedimentary surface, and the effects that the microbes have on deposition of sediments, changes the physical system in a clastic setting. Meaning, normally a clastic depositional area is governed by erosion and deposition, and there is literally no big moment in between those two conditions. A grain is taken away, transported, and deposited. So it's really never really quiet. But if a microbial mat grows, a biofilm, then erosion is reduced, deposition is influenced in different ways. It's too complex, I don't go into detail here. But what the biofilm does, it constructs its own dynamic window so that it's comfortable with its situation on the substrate. It's not ripped in pieces, it's not covered by sediment at all. It's a way of bioconstruction. So just another thing for geologists, that the MISS are classified as the fifth group of primary sedimentary structures, which is called bedding modified by biofilms and microbial mats. So it's an own group in the classification of clastic lithologies. But it's not quite as simple that only erosion and deposition affect MISS, the shape they have. There are many different ones. Also, the climate plays a role for various reasons, as we will see. So there are varieties. There are cold climate varieties, semi-arid hot climate varieties, and humid hot climate varieties. This is the Nama group in Namibia. It's a Neoproterozoic in age. And around that time, this area that we studied, it was a very cold climate, almost polar. Cyanobacteria, or what was probably cyanobacteria, they don't mind cold temperatures at all. We have in polar lakes and in polar valleys and so forth, wherever, there are very thick microbial mats in the Antarctic, so they don't care at all. And so typical cold water MISS would be wrinkle structures, here two types. You see that's actually in situ lithified microbial mat. It can happen under very specific circumstances. I talked about this yesterday, this entire taphonomic path, how actually a structure like that can become fossil. It's an anomaly in the fossil record. It doesn't happen very often at all. So that would be a cold water variety here. So if we would take a closer look on the thin section, or what we see sedimentary grains and then some pyrite and stuff that records the presence of some microbes in their fossil ones. Then this here is semi-arid here. That's actually not Archean. It doesn't matter. We see the same in Archean deposits. That's Triassic, but it could be the Dresser Formation in Western Australia as well. It looks exactly the same. And what we see are things like PTs. It's not TPs, it's really PTs, that is not my mistake. So someone came up with this word, PT, and someone said it's a pity with the PTs, but all right. So what that is, it's those cauliflower-like elevations that you see us on the right side, this orange photo. We look down onto a microbial mat, and a typical student beginner always has the scale in the center. So you see this is an old photo of mine. And your students do that. Your students do that too, right? So it's a Swiss knife for scale there. And you see this cauliflower arrangement there. Those are microbial mat surfaces. The microbial mat grows laterally. The biofilm grows laterally. And inside, evaporite minerals start to form, they crystallize out, and this crystal pressure leads to this updoming of the microbial mat surface. And then on the left, you see the same thing in the fossil. I don't know what that just was, but it's not there anymore. So then, Then here, Tunisia, modern Tunisia, an example for a tropical climate. We see tufts here on the lower left photo. It's a lateral view, a close-up view onto a microbial mat composed of cyanobacteria in a Zapka setting, actually. And we see those triangle-shaped elevations. Those are tufts. And they are completely composed of filaments of cyanobacteria that grow along each other or move along each other upward. It is, again, a stress response to desiccation. And on the upper right, we see that those are actually preserved in situ. Basically, the entire organic substance of the microbial mat lithifies and it becomes a mineral. In this case, it was aragonite that then recrystallizes very quickly into calcite or dolomite, depending on the situation there. So that's a close-up here on the upper right photo. You see filaments, and they are encrusted. They are already dead, but their outside is encrusted, in this case by halite. And in the lower left, you see some calcite forming, not where the microbes are, but where there were gas bubbles. So the gas is lithified into a calcite. Quite interesting. You've seen this yesterday. That's just different structures and their names. So where does fossil microbenthos occur? I mentioned that yesterday again, but already, but here once more. So we need, if we go into the fossil record to South Africa, we need to know where to look for those structures. We can't just go and hope for the best. And we are able to identify exactly where we will be able to find fossil MISS. You don't see them very well in the rock record. They're very, planar. They have no specific color. It's just some crinkles somewhere on a sedimentary surface or something. So you just have to know where to go. Otherwise, you look forever. So on the left side, you see the ecological window. If I take now a specific look at microbial mats composed of cyanobacteria, we see that those microbial mats prefer substrates that are composed of predominantly very clear quartz grains. One reason is that those microbial mats incorporate the quartz grains as a response to deposition, and those quartz grains inside a microbial mat functions as lenses. They bundle light and lead that light straight into deeper areas of the microbial mat, and the autotroph part of the microbial mat, the cyanobacteria, that layer can grow much thicker by this process. One reason out of others. So it has to be a clean sediment. There is not much suspension in the water. We know the same thing from reef-building corals. They have zooxanthella, meaning reef builders avoid very suspension-rich water just because there's not enough light arriving on the seafloor. And also the wave energy and so forth has to be moderate. More about that in a moment. On the right, that's the taphonomic window I mentioned before. We see that only very specific sedimentary events that take place in a chronological order can lead to the preservation of a microbial mat. So first of all, we have to have this nice clean sand a microbial mat can establish. It's not an erosive area, it's not too much deposition takes place. Then, however, sediment has to be deposited on top of the microbial mat, and the amount of sediment has to be so much that there is a layer forming so thick that the microbes cannot migrate anymore because they don't see the light, and the layer is too thick, so the microbes cannot migrate up and give up the microbial mat, so they can't do that anymore. They are really buried for good. That sediment has to be finer than the sediment on which the microbial mat is growing, because if it would be coarser, that would mean the erosive forces have to be stronger. But if you have erosive forces like flowing water, waves is even worse, they would erode that microbial mat. So you have to have a layer a depositional environment where the erosion has to be lower, otherwise you destroy what could potentially be your fossil later. And then later on you must have a substantial amount of sediment deposited again that triggers the lithification processes, diagenetic mineralization of organic matter in situ. So it's really very rare that all that happens in the correct succession. But that's our taphonomic window. So we need to have events in a rock succession where we can see that, and where we have an ecological situation and a taphonomic situation overlapping. That's where we hopefully find our fossil. The MISS are distributed through the entire record, Earth history, with the oldest, of course, as I mentioned, is in Archean rocks. So here, what I like just to point out is the microbial mat lithophages. This looks completely complicated, but I will not bother you. Here in the center, if you are geologists, you are interested in finding MISS, you need to keep this in mind. There are rock beds in rock successions that are sandstone. It should be fine sandstone, that's always the best phases, fine sandstone. Fine sand, the grain size is optimal for cyanobacteria to build a microbial mat. They can move, they're not adhering to any clay or anything. And it has to be clean quartz, so 96%, 98% quartz, nothing else. That's good. Small ripples on surfaces indicate you that is a good setting because of currents crossing the sedimentary surface right in the right amount to take away fine material without eroding really the sand. And the rock layers themselves should have thicknesses of 2 to 20 centimeters. So that's the dynamic setting that we need for microbes to establish. So now where do we find those wrinkle structures in MISS? Here an example, that is a continental shelf. Here a fossil one, and we were able to identify different types of MISS in different phase zones, like for instance in a lagoon, that's this area here. So in the upper right corner, so this here is a lagoonal area. Those are little overwash fans here. I have to show this to you too, one moment. So here, that's one type here. Those are overwash fans here. Those are big overwash fans that go all the way down the continental slope. So the areas of those settings which are not active anymore, you wouldn't find a microbial mat in a ocean canyon somewhere, but in areas that are not so active, that's where the mats grew, and that's where we find then fossil MISS. So now some examples from the Moody's group, South Africa, that has an age of 3.2 billion years. That's how the rocks look like in the field there. The material crops out in South Africa, close to Swaziland, and close to this famous little town Barberton. So the Barberton Greenstone Belt is it's a rock succession of different types of rocks. It's a wealth of information on the earliest fossils, and it is especially the Moody's group that includes clastic sediments and then attractive things like that. That's a wrinkled structure. You barely can see it. So that is something that looks almost like the skin of an elephant covering a sandstone. That's what we are looking for, very attractive, isn't it? But sometimes we find things like roll-ups. On the lower right, it's a fossil, lower left is a fossil. On the right is exactly the same thing from the modern. So that's a rolled up sandy layer. And as you know, sand is composed of loose grains. You can't really roll that up, not even if it's wet. There's no mud involved, so we know, oh, this is a microbial mat bound, especially if we find fossil microbes in there. That's another surface, rippled surface that showed a microbial mat colonization. So in vertical section through a fossil sandstone surface, which includes a microbial mat, we see things like that. So those dark lines are fossil filaments, and they include what we call oriented grains. We must not bother really about this word, but those are grains that function as lenses to channel light into deeper areas of the microbial mat. So we have fossil filaments, not very nicely preserved. They look actually pretty awful. If we take a look at it under the microscope in a close-up, it's basically those filaments, filament-like textures that we only see because there's pyrite and some carbon particles, little dots arranged where the original filament was. So we don't see things like cell walls, and that's all gone. But we see the textures of the microbial mats, and we see those things like oriented grains and other things. So Witwatersrand supergroup, South Africa, a little bit younger, that's 2.9 billion years, and it's located in the Kapwal Craton, close to the city of Klerksdorp, and of course close to Johannesburg. That's how it looks like. One pathetic thing with sandstone is that the outcrops are terrible. If you look for carbonate rocks, you see, nice walls and nice layers. You can walk along the rock layer for miles. In a sandstone, it's not the case. That's what you get. That's your outcrop. And then we have to figure out what happened here. So the Brixton Formation, as part of it, is again a shelf setting. We can distinguish different facies zones, the lagoon, a barrier setting, the proximal shelf, the distal shelf, and here we have different MISS recording different types of microbial mats. Not only MISS, but others as well. Not only wrinkled structures. So on the lower right is a wrinkled structure. On the on the left, that is just a fracture pattern. And I'm not talking about this big fracture that you see, the dark one with this straight line. That's just a crack in the rock. I'm talking about this kind of loop that you see in the surface. It's this one here. You might have to take a look, closer. So this one here. And then erosion remnants and pockets, which are indention in an otherwise planar sedimentary surface. So you can tell already those microbial fossils are very unattractive, very unassuming, and that's why people never really saw them. You have to know what to look for. A stromatolite is pretty obvious. So the MISS occur right at areas, especially we could find this in the Brixton Formation, right at areas where the sea level switches from being transgressive to regression. Large areas of tidal flat and shallow shelf are forming. That's ideal for microbial mats to develop, and then the mats are being buried, and we have a lot of MISS. So with those great examples of really some of the oldest fossils, I like to finish. That's a book that I wrote, and I'm always telling people, you do not need to buy it. I'm not advertising my book to get rich, because I will not get rich even if you all would buy it. But you should read it because it's interesting, I think. And thank you.
Excuse me, how do we get your book? Here. Over here?
Internet.
You just download it?
Yeah, so there is an e-version. Don't ask me for the link, I don't know, but I know there's an electronic version or Amazon.
Okay, thank you.
Uh-huh. Or ask your library to buy it and then rent it.
So thank you for the nice talk, Nora. Questions?
I hope it's not super stupid, but I think like if we know exactly or if we have an idea about what metabolism or kind of bacteria form the microbial mats in the Archean time, it has a huge implication on environmental conditions on at least in Archean, whereas there is a lot of discussion about it. So I was wondering if there is any proxy. I know you mentioned like the presence of pyrite and these kind of things. Mm-hmm. If there is like any proxy that we can see and to go forward than actually microbial mats, like know if there are cyanobacteria or maybe an oxygen photosynthesis, or if there is any proxy that can give us this kind of information.
Yeah, so if we take a look at Archean life and we are really bone honest with ourselves, we cannot say it was this particular group of microorganisms. I hope I haven't, but maybe I did. I might have been very generous with the word cyanobacteria, even I was talking about the Archean. Shame on me. I don't do that, at least not in my papers. So we don't know what they are. It's impossible to say cyanobacteria as we have them nowadays were around in the Archean already. That would be 3.5 billion years of no evolution in a prokaryote, and that can be. We also have to go away from thinking of species at all when we talk about prokaryotes, because as you know, there are no species in prokaryotes. There are ecotypes or genotypes, things like that, but not species. The microbial groups, maybe, but what we can say is probably they were already photoautotroph, because they occur only at those very, very specific environments where the sediment tells us there were the conditions that today allow cyanobacteria to form microbial mats, clean water and all that. That's why I have to go really into lithology and figure out what was the environment exactly from the point of view of a microbe. That's why we measure grain by grain and orientation of grains and all that to figure out what was the setting. Once we have photoautotroph bacteria and they die, the logical consequence is that there are heterotrophic bacteria, and it doesn't matter who they were. People always say, well, there were sulfur reducers in the Archean. Well, we don't know. There was something. A typical mineral that's forming when you degrade organic matter is pyrite, so that's not a big surprise. We know that, especially in a more anoxic setting. But there are other minerals, hematite, camosite, and so forth, that form, and those are replacement minerals. Basically, the organic matter, the biomolecules of the microbes are cracked into increasingly smaller parts, little, like bricks, smaller, 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 until the bricks are so small that we have really small chemical compounds or even elements, and they react with anything that's around in the seawater, and then you get a mineral. That's the effect. And sadly, a sandstone or sandy substrate, those early diagenetic processes take place within hours, maybe a couple of days, goes very quickly, and the organic matter is gone, even in an anoxic setting. So I was about to go, I forgot. Anyway, so that's the information we have. And really, once you have all those little elements and chemical compounds, we really have not the information anymore to say it was that original microbial group. And there are people who try to find fossil biomolecules in Archean rocks, and I may say that because I talked to Roger Summons, who is one of them, and he says, honestly, it's not possible, because if we measure something in a rock that is a biomolecule, it's something more modern. It must not be a lichen or something that grows right now on the rock. It can be a fungus or something that migrated into the rock 400 million years ago during the Devonian or something, we do not even know. And that's younger, and that can be preserved, but we don't know what was originally around. So the other thing is that biomolecule, as you know much better than I do, they are unstable. Those are big molecules. You need to have energy to hold them together. Once life is out of a biomolecule, it just falls apart. Those rocks are very old, 3.5 billion years. That is, if you count each second from Christi birth to now, each second is a year, that's the time, meaning a biomolecule doesn't sit there for 3.5 billion years and doesn't decompose. It's technically not possible. So one has to be very careful with any interpretation. What were those organisms? Yeah.
Any more questions?
Nora, I'd like to know, please, you talk about the EPS changing the direction in according to the current. Does it apply to microbial mat as well? Does it, or it's only for biofilms?
Yeah, so a microbial mat is a biofilm.
Thicker one and more
complex. Yeah, it's just bigger.
And that works for example, for stromatolite as well. We can think that.
Yeah, exactly, yeah. And it depends what kind of current you have. If you have a current, which means water crossing a sedimentary surface, it is of laminar character. Physically, in a natural environment, there is no laminar flow, but it's more laminar than water, which is turbulent, like in a wave. So what the microbial mats do is, with their EPS, they cause a more laminar flow of the water crossing a surface, and by doing that, they reduce the erosive force of the water. First of all, so if you have water eroding, that's one thing, but if there are grains in the water, the grains are what we call erosion weapons, meaning a grain that bangs on the surface has even an increased erosive effect. So if the microbes clean the water by baffling and trapping, by combing out suspension, they take care of this, of the erosive weapon. So it's a laminar flow, it's clean, the erosion is strictly very strong reduced. So they are able to reduce, to change turbulent water and create a laminar flow. That's this dynamic window we can reconstruct by taking a look at the rocks and sediments. And we did field experiments too, and so forth. Yeah, and the EPS basically just switch. They're like, oh, alarm, and yeah.
Okay, any more question or opinion? So let's move to the next speaker. First of all, well, I would like to inform you that our next guest speaker, unfortunately, is not here. The Professor Thomas Fairchild. He has a problem in his family, in health problem, so we apologize in name of him. So let's to the next speaker, the Professor Evelyn Sanchez Bizan. She has a degree in biological sciences at Universidade Metodista de São Paulo, Master in Geosciences at University of São Paulo, and PhD in Geosciences at University of São Paulo too. Now Evelyn is a professor at Universidade Federal dos Vales do Jequitinhonha e Mucuri at Diamantina, Minas Gerais, where works with paleontology, especially with Precambrian paleontology. Today, Evelyn will present the talk, Early Biosphere, Microbialites and Microfossils.
Thank you very much. Okay. Hello. Well, I don't know where to stay. I think I will follow Nora and stay here. Well, first of all, thank you very much for inviting me. That's a pleasure to be here. That's not a talk about original results of a research. Actually, I try to put together what we know about early life, what the fossil record shows us. So, and I know that here we have people from chemistry field, biology, physics, so I tried to be the more didactic I could be, okay? So let's go. So we're gonna talk about early biosphere, microbialites, and microfossils. So I'm gonna tell you about biosphere, Archean biosphere, and Archean, a little bit about Archean and Paleoproterozoic, that transition, what do we know about the fossils in this transition here, in Archean and Paleoproterozoic. But before we talk about the early biosphere, I think it's important we know a little bit more about the paleo environment where this biosphere habitated. And it's even more important to keep in mind time involved in this situation, in this early biosphere scenario. So I will start by time, then I go to paleo environment, and then we're gonna talk finally about biosphere. Well, about time. Here we have a nice picture. I really like it. I show them to my students every semester because it is colorful and full of nice fossils. And this picture shows us the history of Earth since the formation of the planet here at the center, and all the events, mainly in the biosphere, that occurred through time until up to now, when hominids appeared. What we can see here, so we have the formation of Earth, we have the appearance of first cells, and the appearance of algae, and then the appearance of vertebrate, plants, dinosaurs, and finally man. And all this time involved here, since the formation of the Earth, through up now, we call geological time. Geological time, or tempo geológico in Portuguese. And in order to organize this time, research have divided the geological time into geological time scale. So what we have here is the International Chronostratigraphic Chart, the most recent one, where we can see the geological time divided in big slices, called eons, and then each eon is divided in areas, and then areas is divided in period, and so on. And what we can see here, we have three huge slices of time called eons. We know up to now Archean eon, Proterozoic eon, and Phanerozoic eon. The Archean eon is the oldest one. That dates back 4.0 billion years and marks the beginning of geological record. And then we have Proterozoic, and Archean lasts from 4.0 to 2.5 billion years, so it's almost 1.5 billion years. Proterozoic lasts 2 billion years, and Phanerozoic, look, only 0.5 billion years. So Phanerozoic is much, it's a small slice of time, but you can see we know much more about Phanerozoic than about Archean and Proterozoic. And why that happened? Because the fossil record, the geological record is much more better preserved than in old times. We're gonna focus here in the Archean eon. The next slides. Well, keep in mind that Archean and Proterozoic appears here very small. Did you notice that? Archean, Proterozoic, and look, Phanerozoic. But when we put in the scale, what we have is Archean and Proterozoic last billions of years, and the Phanerozoic is just that. But realize the fossil record or the geological record, or the outcrop one, sure. So we know much more about this small slice of time than we know about this one. Okay. Concerning the paleo environment settings, what we have in Archean, during Archean, was an early atmosphere, thinner than we have nowadays. Today, the atmosphere reaches 1,000 kilometers or even more. And by the Archean time, during the Archean time, it's just 60 kilometers thick. And it was composed as a model by casting, and it's still valid. So what we have during Archean times in the atmosphere was a very rich CO2 atmosphere, atmosphere rich in CO2, and also nitrate, water, molecular hydrogen, and just traces of oxygen. And we can see here the partial pressure of CO2 decreased through time, mainly during periods of glaciation. And if we think about glaciation, we know that that's the moments where O2 raised and the CO2 decreased in terms of concentration. Well, and also we have this model by Kathleen and Claire from 2005. And what we have here is the sources of gases for atmosphere. Here in the Hadean Archean times, we can see methane, ammonia, molecular hydrogen. And then after the differentiation of nucleus, mantle, and crust, atmosphere was filled with water, CO2, NO2, and other oxidative molecules. And concerning the lithosphere, what we have are three models. One composed by a huge continental crust, another different continental crust, but of huge scale, and a 3D model that proposes the lithosphere was composed by small plates of continental crust. We know that through greenstone belts and TTGs, rocks preserved in craton areas, and we're going to see that most of fossil records are in those greenstone belts. Well, that's just, I like this picture. I showed to my students because it put together all we know about the idea. So we have a lithosphere, primitive atmosphere, and, well, I just knew this morning about the heavy bombardment event that it's not occurred. Okay, so actually research proposed that we have two moments of heavy bombardment events, one in the Hadean and another one in early Archean time. So that must be play some role on the fossils, on the biosphere, the early biosphere. Well, okay, so now we're going to move to biosphere. We already know the paleo-environment and the time of early biosphere. And now we are going to focus on biosphere itself. What type of fossils do we know up to date? We know that fossil record may be formed by paleovertebrates, paleoinvertebrates, paleoplants, paleobotany, micropaleontology, microfossils that are only fossils smaller than 2 millimeters. We have this area called paleoichnology, which studies trace fossils, not fossils itself, but trace fossils, and chemical fossils as well. In Archean time, what do we have? Which types of fossils we already know from Archean times? We already know microbialites and microbe-induced sedimentary structures that Professor Nora just showed us. In Archean times, we also have microfossils and chemical fossils, which are under discussion. I'm going to show you the first one, the microbialites, and what we know about microfossils of Archean times. Well, concerning microbialites, what we know is that they comprise bioconstructions formed by microbial mats in underwater environments, marine or lacustrine or deep sea, shallow waters. Well, the important is to have water, and they present this laminated aspect formed by microbial mat growth. So as Professor Nora told us, the microbial mat, the microorganisms try to escape the sedimentation input that might be that can be precipitation, sedimentation, or trapping by sedimentation. Well, that's not an Archean one, that's a new Proterozoic microbialate, but it's very didactic. We can see here the lamination and the growing direction, and then the ramification. That's a very nice picture. Well, microbialates exist up to now. Nowadays, these ones are from Australia, Shark Bay in Australia. And here we can see the microbial mats. Okay, and microbial mats grow by precipitation or trapping by sediments. So we have all this competition between biota, microorganisms, and sediments. So that that forms the lamina, then will form the stromatolite, the microbialite. Well, the problem is that we know that stromatolites are formed by microbial mats and microbials. The mainly microorganisms that forms microbial mats are cyanobacteria. But the problem is that in Archean rocks, we don't have any trace of cyanobacteria. We have stromatolites, we have microbialites, but we don't have cyanobacteria. So, can we use the present stromatolites as a model to study Archean stromatolites? That's a problem we have. Well, stromatolites develop, can show lamina of stromatolites and microbialites can show different morphologies depending on the paleobathymetry, the light and sedimentation influx. So they can be laminites, so flat planar, lateral stromatolite microbialites. Here we have a column with process, it's in Xeria. Here we have domical forms. Oh, here we have my favorite one, conophyton. It's conical, indicative of very deep, of deeper subtidal waters. And here we have a nice one where we can see the lamina and then the stromatolites ramification, and then here a ramification, then become getting together. So, if you want to see Archean stromatolites, you can visit South Africa, you can go to Australia, or you can go to North America. And we have small occurrences, less expressive occurrences in India and in Russia. And how they look like? Well, that's the oldest occurrence of a microbialite. It's recorded in Ishua supracrust belt in Greenland. It has 3.7 billion years here. But this occurrence has a little problem that Professor Nora already told us. It is recorded in a metamorphic rock. So that might be a problem. Okay. It was identified by a research group from Canada, and in 2000, I'm not sure, but 2016, yeah. But another group from Australia already published a paper discussing these occurrences, so it's under debate. Okay. Well, it has associated, these microbialites are associated to cross-lamination in tepestite breccias, so it's indicative of shallow marine environment. Another interesting occurrence of microbialites in Archean times are there in Australia with 3.4 billion years and show domical forms, conical forms. Oh, here another domical dome forms, and a wide range of lamina shape. So, if lamina change according to the environment, that indicate that these fossils from Australia of 3.4 billion years occurred in a wide range of environment. Actually, they occur between very shallow waters, or shallow waters to subtidal waters. Here you can see the conical shape of some microbialites of Australia. And when we come to younger occurrences in the Archean, what we see is different types of morphologies. So we have columns, well-developed columns. We have these lateral linked domes, planar microbialites. So the morphology is more varied. Okay, so be careful, because what you see, it's a constant occurrence of microbialites in Archean rocks, but we are tempted to say, okay, through time, microbialites presented more different morphologies than the older ones. But we need to be careful, because we are dealing with fossil record. So the fossil record presents serious gaps. So this can be a dangerous interpretation to make. And concern the microfossils, what we have is this occurrence also, in the Nuvakituki belt in Canada. So it comprises filamental cells. And it has 3.7 billion years. Another interesting occurrences also comes from Australia, 3.5 gigas from Pilbara craton, where we have coccoidal cells and filamentous cells. Oh, and we also have these occurrences. This looks like a cell, but actually that's a mineral. So we need to be very careful when we study microfossils, very old microfossils, because some minerals can mimetize cell shapes. And we also have these occurrences, the microfossils of apex shark in Pilbara craton. It has 3.5 billion years. It was interpreted originally as cyanobacteria, but some research is not in accord with this interpretation and reinterpreted these structures as self-organizing structures. So it's also under debate. Maybe we have here it's dubio fossils. And we have this interesting occurrence in Africa with 3.3 billion years. Here we can see cells and very nice. Ooh, what we have? Okay. Here we have cells, and some of them was preserved during the division process. Here we have modern ones to serve as model, and here we have the fossil cells. Very nice occurrence. So when we put the data together, what we have is that since from 3.5 billion years through the Archean, we have 6 different morphotypes of microfossils, include rod-shaped microfossils, small coccoids, large coccoids, filaments composed by cells, or tubular filaments. We have a continuous record of microfossils in Archean, and they were found in a wide range of environmental settings. When they were found associated to microbialites, or they represent planktonic forms, benthonic forms, associated to non-determinate marine environments, lacustrine environments, associated to volcanic environments, hydrothermal vents, and the case of apex shark that is associated to basalt rocks. So when you put all these two informations together, the age and the type and the environmental settings, what we have, okay, here's the Archean from 3.7, that's the date of the oldest fossil record, to the end of Archean, and what we have is first forms occurring, the older forms occurring in hydrothermal vents. Then we have forms occurring associated to volcanic environments, followed by forms in marine environments, associated to microbialites by the end of Archean, and associated to lacustrine also in the end of Archean. And just to remember, microbialites are known since for 3.5, 3.4 billion years. And sure, there was cells forming those microbialites. We just haven't found the microfossils yet to put this box here. So that's very tentative because, sorry. That's very interesting because the oldest forms of the oldest microfossils, they occur associated to hydrothermal vents. And if you remember the lecture by Dr. Russell, that's probably the cradle of life, the hydrothermal vent. So it's very nice. That's nice, but that's tentative. To interpret this fossil record, okay, life was born in hydrothermal vents, so it's expected to find the oldest form of life in hydrothermal vents. It's very tentative, but we need to be very careful because that's maybe a matter of we haven't found fossils in another type of environment settings. Okay, so here. And by the end of Archean, what do we have? We have this occurrence, very interesting occurrence, that's gunflint biota. It was found in the Lake Superior area near the boundary between Canada and USA. And it's formed by microfossils of interesting morphologies. Here we have coccoidal forms, filamentous forms. We have this here, Eosterium, very nice shape of, looks like a star. And here we have this microfossil, very interesting, Cacabeckia umbrellata. That's my favorite microfossil ever. So we don't have anything that look like this Cacabeckia nowadays. So the gunflint biota occurs associated to banded iron formations we call BIFs. It dates from Archean to Paleoproterozoic age. Are composed by organic walled microfossils, so microfossils with which wall is made mainly of carbon. It occurs in a subtidal environment. 16 taxa were identified, and 2 biotas, one associated to stromatolites and another it's planktonic. And from these 16 taxa, 6 of them was not identified in terms of biological affinity. So it's very interesting. Why? Oh. Because we need to remember that life, during the evolving, changes information not laterally with another groups. So if we back in time, maybe what we see, it's other type of domain of life, not only eukaryotic, prokaryote life or archaea, but another type of domain. So it's very nice that may be a window to another group, unknown group. And the gunflint biota, as I told, is preserved in banded iron formation, a type of sedimentary rock very common during the Archean to Paleoproterozoic times, and it indicated the origin of photosynthesis and so the oxidation of a atmosphere, because these iron formations only formed in the presence of oxygen. So we can see the banded iron formations start here between 0.4 and 3 billion years ago and lasts to 2 billion years ago. And we have a small occurrence here by the end of Neoproterozoic during the glaciations, later Neoproterozoic glaciations. So this moment here, when we have the appearance of photosynthesis and the oxidation of atmosphere, we call this GOI. So it's the Great Oxidation Event. So just to summarize, during Archean, we have early atmosphere, continents forming and also crustal rocks. And we have the heavy bombardment event that maybe shaped life. And what we know up to date is microbialites with cells associated, coccoidal cells and filament cells. We need to be careful because what we have, what is preserved, it's only forms. We don't know the metabolisms. So what we do is to use a dualism. So we interpret the fossil record according to what we know nowadays. But that might be a problem. And also what we know, it's a non-conventional fossil record represented by gunflint biota. Okay, that's how I was looking for this slide. So when we think about evolution of life, what we have, it's not branches, regular branches during the evolving events, but what we have is a net. Life evolves as a net. So if we assume time is going this way, right? We are here nowadays. When we go back, maybe Archean is here. So what we're going to see is not prokaryote, Archean, bacterial domain, but we may have another type of domain of life. So I think that's what makes Archean fossil records so interesting. It's so difficult to study as well. And we also need to remember that all the life we know, we put in 3 different domains, but it's just a small part of extant life nowadays, and this extant life is just a small part of all the life that ever existed. So we have a lot of work to do when we think about Archean fossil record and early life. Okay, that's what I have to tell you. Thank you very much.
Thank you very much, Evelyn. It was a nice talk. Any questions? Lucy?
Hi, Evelyn. I'm Alice. About the description that Flavia gave about your CV and everything. So I was wondering if you can tell us a little bit about the microbiolites that you have been working with in our Archean on Paleoproterozoic Brazilian record. Because I was really curious if you can really see something. I don't know anything like Nara was saying that it might be impossible for us to search for microbiolites or microbomats in metamorphosed rocks. And almost all the Brazilian record is at least metamorphosed at green sheets faces. So I was wondering if you were finding something, if there is any interesting that you can share with us.
Nice question. Actually, no problem. Actually, my studies are focused on Neoproterozoic microbiolites, meso to Neoproterozoic microbiolites. But recently, I started a project along a research group from Ouro Preto University. And we are studying, I know someone would ask me, so I put these maps here. And here we have, that's data from Geological Survey, Brazilian Geological Survey. And here we have Paleoarchean rocks. So we have this interesting occurs here in the state of Bahia. And here we have, Mesoarchean rocks. So we see it, the record improves a little bit, and Neoarchean, and some terrains of uncertain age. But we know that somewhere in between Paleoproterozoic and Archean times. Well, recently we started to look for signs of life here in number 4 area. That's Galvão block. In the south state of Bahia, that's Archean, Paleoarchean, and that's complex gavion here. We have greenstone belts with nice chart occurrence, and it's very well preserved and present metamorphic signs, but low metamorphic, not so high metamorphic grade. So we are very enthusiastic, but it's totally. How can I say in English? But muito no começo. It's just starting. We are just looking for something, okay? But we have nothing solid up to now to present.
So I have been working with actually your point. I don't know what number is that. I don't know, but I'm in Minas Gerais state, which sequence for Rio das Velhas greenstone belt. And we have rocks metamorphosed at low green sheet faces. And I actually can see primary structures preserved. I don't have the knowledge to look for microbomats or anything like that, but I can see sedimentary primary structures. So I have this perfect bundled everything, like shirts and iron formations and everything. So it's a place to look for. And yeah, you have been worked there too, right? No? Yeah.
But I think you can find stromatolites.
Oh, yeah. Yes. Yeah. Yes, please.
Yeah, if I just have a remark. So lower green schist
That is normal. As soon as you have, the primary sedimentary structures or the primary rock bedding visible, you can look for fossils. What I meant was really the real metamorphic rocks where you do not have anything. It's even new minerals that form because of high pressure, like real high pressure, high temperature. Then you don't find fossils. You can try, of course. But lower green schist, that's normal. And a lot of lower green schist is actually not only metamorphosis, it's just the sheer age of rocks. We don't really think of it, but rocks do age. So the crystallinity of a mineral changes by sheer aging. It's a thermodynamic process, and what you have is in a really old rock, the Archean rocks, the greenstone belt rocks, they have really large crystals. But you still see, there were ripple marks and so forth. So that's possible, yeah. But
I
not
can actually
like,
see ripple marks, so yeah.
Yes, yeah, no, you're good.
Okay,
And
awesome.
chart
Thank you.
levels are of great interest in chart because they are very strong. They are not susceptible to metamorphic so easily. So I think I take a look at chart levels. Chart levels. Okay.
Thank you.
Just enjoying the discussion. Alice, I have a question for you. What about the isotopes, biosignatures, in metasedimentary or more metamorphized rocks?
Oh, yeah, awesome. Yeah, actually, I gave a talk yesterday on the San Francisco Creighton meeting about how it's actually now possible for us to interpret like biosignatures in like not a lot of metamorphism, but at green sheet faces, maybe on fibrillite faces too. And we can actually now interpret with, if we use like a multi-proxy approach and put everything together, we can actually understand a little bit more about biosignatures in these affected rocks by like hydrothermal alteration or other kinds of alterations on the rocks. So I will show during my talk that we are interpreting actually biosignatures and atmospheric conditions and green schist face rocks using carbon and I'm not showing the nitrogen today, but carbon, nitrogen, and sulfur. And it's possible to consider how the alteration is going to change your fine signature. And this is why like we have to go always like further with analytical development. So advances in methodology are really important in this case, because as far as you go with the precision of your sign, it's easier for you to interpret how alteration can like change it. And considering the alteration, you can actually interpret biosignatures. So I don't know if I answered it. Yeah.
Thank you, Alice. More questions? So we will finish this topic.
Keep that.